pleasure to extend warm welcome and hearty greetings to all the distinguished guests, eminent speakers, scientists, and professors, delegates, and students who have come together on this e-platform to disseminate their knowledge. India has glorious tradition of scientific temper from Vedic times. Famous natural scientist and philosopher of India, Kanad of 4th century BC, in the 10th chapter of his treatise Vaisesik Darshan says, Drishtanam Drishta Prayojananam Drishta Bhave Prayogo Bhyudayaye, means the path of prosperity is led by experiments seen by ourselves, carried out to shown to others, or to go deeper to gain more knowledge. Without experiments and mathematical computations, it is not possible to prove scientific results in modern era while maintaining social distancing due to COVID-19. These growing combinations of extraordinary computational efficiency and articulate automated laboratory equipments with artificial intelligence will make possible even more advances and applications in the coming years. I am very much thankful to all guests of inaugural session to join with us. I am very much thankful to Mrs. Hema Sudesh Deshmukh for her cooperation in every program of our college. It is not possible to organize such a conference without the outstanding support of our patron and principal, Dr. Sumen Singh Baghel, Madam. So, thank you very much, Madam, to you also for supporting us. The conference has received good response from delegates from 9 countries: Malaysia, South Africa, Palestine, Albania, Kosovo, Saudi Arabia, Morocco, Uzbekistan, and 18 states of India. The registration of total participants is 685. I hope all of your active participation will make the discussion more lively and fruitful. Thank you very much.
Thank you, sir. Now I would request Dr. Dakeshwar Kumar Verma, sir, Assistant Professor Chemistry, Government Digvijay Postgraduate College, Rajnandgaon, to deliver his note from the desk of Organizing Committee. Sir. Thank you so Thank you so much, sir. For the welcome address, I would like to invite Dr. Suman Singh Baghel, ma'am, Principal, Government Kamla Devi Rathi Girls PG College, Rajnandgaon. Ma'am. And Mike.
बघेल मैडम आपका माइक बंद है।
सुनो ये ले जाओ पंखा चलो मैं सुन रहा हूँ ना
जी सर।
अब आवाज आ रही है मैडम?
हाँ आवाज आ रही है, अब आ रही है।
Good afternoon to everyone. It is a matter of proud privilege that the Department of Chemistry of Government Kamla Devi Rathi Girls PG College Rajnandgaon, Chhattisgarh, India is organizing an international web conference on emerging field in chemistry, advances and applications on 10th to 11th August 2021. First of all, I welcome to today's chief guest, Honorable Dr. Aruna Palta, Vice Chancellor, Hemchand Yadav University, Durg. I am pleased to welcome Mrs. Hema Deshmukh, Mayor and Chairman, Jan Bhagidari Samiti, Kamla College. I also welcome today's keynote speaker, Professor Bhim Al-Rahimi, Faculty of Applied Science, Ibn Johar University at Melol. Invited speakers, Dr. Elior Birdy Burodo, Associate Professor, Kursi State University, Faculty of Natural Science, Kursi City, Kashka Daryo Region, Kuchabok, Uzbekistan. Dr. Kamlesh Srivas, Associate Professor, School of Studies in Chemistry, Pandit Ravi Shankar Shukla University, Raipur. The team behind this web conference are convener and head Dr. Omkar Lal Srivastav, Chairman, Biodiversity Management Committee, Rajnandgaon. Organizing Secretary Dr. Dakeshwar Kumar Verma, Assistant Professor, Chemistry, Government Digvijay College, Rajnandgaon. Joint Organizing Secretaries, Ms. Sonali Loya, Mr. Amit Devangan, Mr. Kuleshwar Patel. It is pleasure to me to welcome all the participants to the web conference from all over India and outside India on behalf of Government Kamla Devi Rathi Girls PG College Rajnandgaon. Conference held great importance in the life of students. They are platform not only to learn new aspects, other perspectives and latest information, but also a good way of networking. This web conference consists of keynote speech, plenary lectures, and paper presentation by established academic expert in the field of chemistry. The main of this web conference to stimulate our participants to explore the latest development, innovation, and application in the field of chemistry. This web conference will also useful for students pursuing post-graduation in chemistry and want to do PhD can learn about the recent study going in chemistry and can explore new area of research. Therefore, we anticipate an energetic and dynamic scientific online gathering. Thanks.
Thank you so much, ma'am. Now, it will be a privilege for me to invite the keynote speaker of the conference, Professor Brahim Al Ibrahimi, Faculty of Applied Science, Ibn Johar University, Morocco, to say few words. Sir, please.
Thank you. Thank you very much. I would like to express my gratitude and be thankful to the committee of organization, especially Professor Omkar and Verma. It's a real honor and a pleasure to meet you. And I would like to say welcome to all audience from everywhere. And thank you. Yes. Thank you so much. I pass the room.
Thank you so much, sir. I would now request our special guest and invitee speaker of the conference, Dr. Ilyo Bardi Murodov, Associate Professor, Kashi State University, Uzbekistan, to address the conference. Sir, please.
Good afternoon, ladies and gentlemen. I am very happy to join your international conference named Emerging Fields in the Chemistry Advancing Application, organized by Department of Chemistry. It's my pleasure to thank us to the committee and organizer of this international conference, Dr. Srivastava, and my friend and Dr. Dakshwar Kumar Verma, and the Department of Chemistry, Government Kamla Devi Razi Girls College. Thank you. Thank you.
Thank you so much, sir. Now I would request the chief guest of the conference, Honorable Dr. Aruna Palta Ma'am, Vice Chancellor Hemchand Yadav University, Durg, to release souvenir of International Web Conference.
मैडम तो फिर वो आ रहा है मैडम करो ना मैडम रोना पड़ता मैडम का यार वो हो गया वो देखिए ग्रीन चल रहा है ये है ना इसमें लगा
Thank you so much, ma'am. Now I would request the chief guest of the conference, Dr. Aruna Palta Ma'am, Vice Chancellor Hemchand Yadav University, Durg, to address the conference with her valuable words. Please, ma'am.
A very good afternoon to one and all present in today's event. It is a matter of great pleasure. The Department of Chemistry of Government Kamla Devi Rathi Girls PG College, Rajnandgaon, Chhattisgarh, India, is organizing an international web conference on emerging fields in chemistry, advances and applications. This is, of course, a 2 days web conference. I recognize the presence of keynote speaker, Professor Brahim E.L. Ibrahimi from Morocco, Principal of the college, Dr. Suman Singh Baghel, Jan Bhagidari Adhyaksha, Srimati Hema Deshmukh. Invited speakers, Dr. Eleor Bardi Murodov from Uzbekistan and Dr. Kamlesh Srivas from Pandit Ravi Shankar Shukla University, Raipur. Organizing Secretary Dr. D.K. Verma, Convener Dr. Omkar Lal Srivastava, all the learned people from academia across the globe, and dear students. I feel honored in stating that Government KD College Rajnandgaon has organized very good quality webinars in this global pandemic time on different subjects of current relevance and on academics too. This webinar is one in the series. Thus, they have proved that they are accepting the challenges of this pandemic time and trying to convert the challenges into opportunities. Today's webinar certainly aims at providing platform to the researchers across the globe to share their knowledges and researches with their fellow academicians. This may further lead to collaborative researches in the core subject along with their other allied branches too. I have gone through the subtopics of the web conference. All seem to be very, very relevant in present context. They showcase the value of chemistry in the well-being of the society as well as in the sustainability of the planet Earth. If well explored, all the emerging new technologies in chemistry have the capacity to open new opportunities and can definitely make the general public understand as to how chemical sciences contribute to make their lives more comfortable and more meaningful. Nanopesticides, nanosensors, microbiome, and bioactive compounds, rapid diagnostics for testing, RNA vaccines, artificial intelligence applied to chemistry, metal organic frameworks, 3D bioprinting, flow chemistry, macromonomers for recycling, better recycling of plastic are some of the very useful emerging technologies in chemistry. I'm sure that this 2 days academic feast will be definitely enjoyed by the academia. I once again congratulate the college for making this event possible and wish that all the further deliberations will be very, very useful for the attendees in enhancing their knowledge in the respective fields. I thank the college for giving me the opportunity to share my views with you all on their prestigious platform. Stay fit, stay healthy, and follow all the SOPs for new normal. Jai Hind, Jai Bharat, Jai Chhattisgarh.
Thank you so much, ma'am. I would like to invite the chairperson of this conference, Mrs. Hema Sudesh Deshmukh, Mayor Rajnandgaon and President Governing Body, Government Kamla Devi Rathi Girls PG College Rajnandgaon, to address the conference. Perhaps there can be a network problem from the side of ma'am. So we'll continue with our technical session. So now our inaugural session have been ended. Without any further ado, I would request the organizing secretary of the conference, Dr. Dakeshwar Kumar Verma sir, to give vote of thanks for the inaugural session. Yes, sir, you are audible. Yes, sir, yes, sir. Thank you, sir. Now, let us begin the technical sessions of day 1 of International Web Conference. For the first session, I would like to invite Professor Ibrahim El Ibrahimi, our keynote speaker, for his talk on the topic the use of computational tools for in-depth understanding of the corrosion inhibition process. Before beginning his session, I would like to give the brief introduction of Sir. Dr. Ibrahim El Ibrahimi is a professor of physical chemistry at Faculty of Applied Sciences, Ibn Johar University, Morocco. His scientific activity mainly focuses on the metallic protection against corrosion using inhibitor compounds, as well as the application of diverse computational tools to investigate the inhibiting process at electronic and atomic scales. Furthermore, he has carried out a series of investigation on various areas of fields of physical chemistry, like electrodegradation of organic pollutants, wastewater treatments, and anti-scaling. He is a co-author of over 50 scientific papers, including review and full research papers, and 4 book chapters as well. He has participated in more than 50 presentations in national and international conferences. He has acted as a lead guest editor of several special issues dealing with corrosion protection. He is also an active review of many international journals and has served as an expert for a research project in corrosion inhibiting topic for King Fahad University of Petroleum and Minerals. From this, I would like to request Sir to begin his session.
Thank you. Can you show me the screen of my laptop? Sir?
Yes, sir.
Can you show me the screen of my laptop?
Yeah.
Please. Thank you. Everything is okay. Did you see the screen of my laptop?
Yes, sir.
Yes, okay. Thank you very much for the invitation. So today I will present for you a thematic about the use of computational tools for in-depth understanding of the corrosion inhibition process. This topic is one of the emerging fields in chemistry, and we will see how the computational tools can lead us to understand how the inhibition of corrosion can occur. So, as you know, in the industrial field, like desalination systems or system cooling or petroleum industrial, the contact of material, metallic material to corrosive environment can favorize the corrosion of metallic. This corrosion is an antifacial interaction with the solution, corrosive solution, and the metals. So to overcome or to mitigate the corrosion, there are many techniques to prevent the corrosion. Among the most used techniques are the addition of corrosion inhibitors. Corrosion inhibitor, it is the chemical compounds which help to mitigate the corrosion or to prevent the corrosion. The mechanism by which these chemical compounds can mitigate the corrosion is by their absorption at the surface. The absorption of this compound at the surface, on the surface, prevent the passage or the diffusion of corrosion species onto the surface. This leads to the protection of surface. So there are many compounds. The problem is how we can explain the obtained corrosion inhibitor. For example, here we have three triazole compound. For example, here this derivative give a good protection when compared to this, and this give up a good protection if you come to the last one. So to explain that, to explain why an inhibitor give a better protection against corrosion as compared to other compounds, we can use what's called the computational chemistry. Why? This computational chemistry can help to understand the inhibition process, because the inhibition process is based on the interfacial interaction between the inhibitor and metal surface. So if we can study the interfacial interaction between inhibitor and metal surface, we can understand or predict the inhibition process. For example, here we have an inhibitor molecules, and the interfacial interaction onto the metal lead the formation of a protective layer. So, until the moment, there are two different approaches. There are two different approaches to study the corrosion, to study the corrosion inhibition. The first one is the quantum at electronic scale. So this approach based on the quantum mechanics, especially in the Schrödinger equation. For example, the method which based largely used they are semi-empirical methods. And semi-empirical methods. There are semi-empirical methods like AM1, EM, PM3, and there are abination method like Hartree-Fock or Malpaissner. So, recently, the corrosion scientists use extensively the density functioning theory based method. This method can help us to understand or to study the inhibition process or the interaction at electronic scale. Another approach to study the inhibition process is by using classical mechanical scale atomic scale. The most used method at atomic scale, they are Monte Carlo simulation and molecular dynamics simulation. And we will see how this works. So, let us begin by the study of the corrosion inhibition at electronic scale. We start first by the global reactivity. So, before studying the reactivity of molecule, we start by the geometry optimization of the molecule. This geometry optimization let us to obtain the molecule with molecular structure with minimal energy. And based on this optimized molecular geometry, we calculate several indicators of reactivity called global reactivity indicator. So there are many indicators, but here I will limit to discuss someone just. For example, here, according to FMO theory, frontier molecular orbital theory, the inhibitor with lower energy gap can provide a better corrosion inhibition. So also by using or based on the HSAB, hard soft acid base theory, we can use some indicator like the hardness to investigate the corrosion inhibition. How? As you know, the metallic materials are the soft materials. So according to this theory, to get a better interaction or between the inhibitor and the surface, the molecule should be softer. So, because according to this theory, soft material interact well with soft material. Another factor largely used is the delta N. Delta N, so the number of transferred electron. Because as you can see here, all these factors are the intrinsic factor related to molecule. And the role of the metal surface, is missed in here. We cannot, the role of this surface is not applied here. So to apply or to intervene the role of metal, we should calculate delta N. As you can see here, is the formula used to calculate the number of transferred electrons between inhibitors and the metal surface. Here is the work function. Approximately 10 years or 8 years ago, the corrosion sensor used here the electronegativity of metal. But when you use electronegativity, you use for one atom. In our case, we have a surface. So to describe the electronegativity of surface, we use this called the work function of surface, and this depends on the Miller index. Another indicator used to take in consideration the role of surface is the first interaction energy. But the problem with this largely applied approach by using just global reactivity is this: we can find some exception or contradiction. Why? Because the corrosion, the inhibition of corrosion is a complex phenomena. So sometimes the sample linear relationship between one factor and the inhibition efficiency is not available. So for this, we need to use more complex model rather than sample linear model. We will see this after. So another explanation why we found such contradiction of some exception is, for example, here you have the molecule with similar structure. If you have the molecule with different structure, for example, here, imagine you have here a long chain or something here, it is probably to do not find the good relationships using the linear sample correlation. So moving now to discuss the local reactivity. The role of the local reactivity leads us to know on the molecule which site can interact effectively with the metal surface. So there are many local reactivity indicators. Here we will cite the most used one as the HOMO, highest occupied molecular orbital, and lowest occupied molecular orbitals. And this gives us the information. For example, here, this orbital, if they are a donation of electron by the inhibitor to the metal surface to form the bonding chemical bond, will be recorded here. And for if your metal gives this electron or charged electron with the inhibitor, this can be occurred via this region. Another indicator of local reactivity of inhibitors is called electrostatic potential. This, for example, here it is the electrostatic potential maps. This can give us the region with rich electron and the region poor an electron. So this map can help us to know which atom or region can interact electrostatically, because when we use HOMO and LIMO, frontier molecular orbitals, here we get this distribution give us the information in which region or atom can share electron. So in other words, the formation of chemical bond with metal surface. But here, the electrostatic potential gives us the atom or the region by which the inhibitor can interact electrostatically with the metal surface. Another indicator of local reactivity largely used is the atomic charge. This atomic charge can give us the atom with a positive charge and negative charge. Generally, in acid solution, the metals are charged positive. So the molecule, the atom within the molecule charged negative will preferentially interact with the metal surface. For example, here, the carbon with the negative charge and azote and oxygen were favorably interacted with the metal surface, because the metal surface in acidic solution is charged positively. Also, Fiqui index. And this Fiqui index can use it to get further investigation on the local reactivity. Here, generally we calculate Fiqui index for nucleophile attack and electrophile attack. More, the absolute value of the Fiqui index, if please increase, the acceptation of electron increase. So, as we see here, before here, we have studied just the molecule, the inhibitor molecule. But the question, or to get a better understanding of the inhibition process, we need to study the interfacial interaction between the inhibitor molecules and surface. So, at electronic scale, this can be done. So the main result using or where we study the interfacial interaction, there are two aspects: the energetic aspect and geometrical aspect. Concerning the energetic aspect, we study or we calculate the absorption energy by this simple formula. This is the absorption energy equal the energy of molecule plus surface, the whole system, minus the energy of surface plus the energy of molecule. So by this formula, we can calculate the energy of absorption. So when we calculate this energy absorption, we can explain the obtained result. Why? Because when the more negative energy absorption mean strong absorption of inhibitor. So good protection. Okay. Another aspect which can be studied by using the interfacial interaction is the geometrical aspect. In other words, the absorption of configuration, how the inhibitor absorbs at the surface. For example, here, as we can see here, they are here on a perpendicular absorption into the surface. So why this aspect is interesting? For example, here we have perpendicular absorption. So here we can the solution of this geometry. We cannot give a perfect coverage of the surface. For example, here you have a vacuum region here, but if you have a parallel absorption, you have a better coverage of surface. So you form a more protective surface. Let us now discuss the solvent effect. The problem with this electronic scale calculation, when we study interfacial interaction, is the solvent effect. In this method, we cannot consider the effect of solvent explicitly, directly, but we can consider this effect implicitly and direct by applying a average potential to your system. Concerning the bond, this method, the quantum chemical method, can give us FDR, the formation of chemical bonds between the inhibitor molecules and surface. But to decide if they are a chemical bond formation, there are two things to consider. The first one is the interatomic distance. So when someone tells you that here they are a formation of bond, a chemical bond, you should take into consideration the thing, the interatomic distance, which should be lower to 2 angstrom, and also the charge surface. Because if you have, for example, the distance is, for example, 2.5 angstrom, and you have not a charge transfer, this means that they are not the formation of chemical bonds. So you should have a charge transfer, either from surface to inhibitor or from the inhibitor to surface. But the main problem with this quantum chemical methods, we study the interfacial, when we study the interfacial interaction, is the time consumption. This method takes much time. It's very expensive in terms of time. So for this, we cannot use the solvent effect directly. We generally work under vacuum. Under vacuum. The solvent effect can take much time for the calculation. But if someone interested in this approach, I invite them to read the paper the work conducted by Anton Kukac, is a professor from Slovenia. He has conducted many studies on the absorption of triazolic, imidazolic compound on the coppers. So another thing is the used method. For example, to conduct interfacial interaction, or to study interfacial interaction at electronic scale, which is more related to the reality, symmetric reality, we should use the corrected form of the FT method. Why? Because if you use simply the FT, The interfacial interaction is occurred by the interfacial interaction considering the van der Waals force. So at the surface, we should take in consideration the van der Waals force, because in a paper recently published, I think in corrosion science, one of the most known journal in corrosion, the author have conducted a sample DFT calculation and calculated the absorption energy. They are not found a correlation between the absorption energy and the obtained inhibition efficiency. But when they consider the corrected form of the FT by considering the van der Waals force, they get a perfect correlation between the energy absorption or absorption energy and the inhibition efficiency of the tested compounds. Moving now to atomic scales. After discussing the electronic scale, we move now to the study of the inhibition process of the corrosion at atomic scale. Here there are two methods: molecular dynamic simulation and Monte Carlo simulation. In reality, the used method is Monte Carlo simulation coupled to simulated analytical algorithm, not Monte Carlo simulation. This Monte Carlo simulation coupled to simulated analytical algorithm. Let's discuss the molecular dynamic simulation. This method is simply we construct our system. Our system contains the metal surface, the solution in which there are the inhibitors, and the vacuum agent. We let this system evaluate in time. For example, here, and here, for example, as you can see here, the evolution of temperature of your system and energy of system for a given time. And after that, we take the structure obtained in the final step here, and we calculate the energy absorption, and we take the geometry of absorption. Another most used atomic scale methods is the Monte Carlo simulated to annihilate. This method is a statistical method which based on the Monte Carlo simulation. For example, here you have the energetic profile of your system. We construct the system, and we put this system in excited state, and we let the system to stabilize. And finally, we obtain many stable many configuration, and we chose the most stable one. Let's now discuss the system. So to do the calculation, we should choose the force field. Generally, in our case, in studying the corrosion inhibition, we use compass force field. This force field contains the parameters of equation, how the equation is resolved, etc. For the no-bounded interaction, in these methods at atomic scales, the van der Waals is considered. Also, the electrostatic are also considered during the calculation. But here there are problems. Here, when we use these methods, we cannot have an information and the information on the formation of chemical bonds. So we cannot use this method to conclude that they are the formation of chemical bonds. Okay, because here when we use atomic scale methods like molecular dynamic simulation or Monte Carlo simulation, here we use the mechanic moleculars, which the electron is not considered directly. So you don't have the overlap of orbitals. You don't have the orbitals. So how you can discuss the formation of chemical compounds and the method don't consider the electronic aspects. So now the simulation box. For example, to conduct this calculation, we start by the construction or to build your system or your simulation box. It's composed from three regions. The first one is the metallic substrate. For example, here we have the metallic substrate of copper, and then the solution. The solution can be simply the inhibitors or the inhibitor plus solution phase. So here, by using the atomic scale methods, we can consider the effect of solvent explicitly. So in acidic, for example, if you have acid solution, we can change here the composition, and we can mimic and similar the acidic solution. And if you have a neutral solution, we can change the composition to have a similar or to mimic the real solution. And after here, you have a vacuum region. Generally, this vacuum should be about 30 angstrom. Why we should this space should be quiet? Because when we do the calculation, we work under the periodic boundary condition. This means what happened in this cell happen in this, happen in this, happen in this, happen. You have a similar comportment here. Why we work with periodic boundary condition? Because if you work simply on an inhibitors on the metals, here you can, for example, if you have, for example, here's the inhibitors and here the metals, and you don't have worked under periodic boundary. This means that you have nothing. So the interaction of the metal with the inhibitor will be correct. So you have to consider the large substance, the large surface. So to consider the large surface, we work under periodic boundary condition. And to avoid the interaction between this box and side box or neighbor box, we should to take create a vacuum region of about 30 angstrom. Moving now on the result. After you're conducting your atomic scale, we move now to the result. This technique can give us generally two things. Is the configuration of adsorption, in other words, how the inhibitor can interact with the surface, and the energy of adsorption. Here we can calculate the adsorption energy by this formula, considering the effect of solution, which is more related to reality. And here, for example, you have here the obtained energy, the obtained adsorption energy. Another feature of this atomic scale based technique is we can consider the effect of temperature. For example, in many studies, the authors or the research found that when we increase the temperature, the inhibition decrease. So how we explain that? By conducting atomic scale, by using atomic scale based method like molecular dynamic simulation, we can calculate the adsorption energy. For example, here the adsorption energy as a function of temperature. So as you can see here, when when we increase the temperature, the absorption energy increase. So this means that when we increase the temperature, the absorption of the inhibitors on the surface become weaker. So this means that you have not the formation of a compact and adherent film on the surface, so the inhibition decrease. Also, we can use this method to consider the effect of inhibitor concentration. So generally, when we increase the concentration of inhibitors, we increase the concentration of inhibitor, the inhibition of the protection ability of the inhibitor increase. How we can explain that? By this method, we can simply study this feature. For example, here we have conducted the simulation in different coverage rats. As you can see here, a general trend is by increasing the concentration, the absorption energy increase. Another thing, by using atomic scale, we can also understand the inhibition process. For example, here we start. I will start by this and finish by this. For example, here, by using this technique, we can calculate the absorption of also the corrosive species, because the corrosion of metallic materials is occurred by some corrosive species. But to this species to corrode to surface need to absorb on the surface. So, for example, here we calculated the absolute value of energy absorption of inhibitors, and here of corrosive species. So, as you can see here, the absorption of corrosive species is very low as compared to the absorption energy of inhibitor. So here we can conclude that the inhibitor have a create affinity to absorb and to deplase pre-absorbed corrosive species. Also, the atomic scale based method can lead us to calculate an interesting factor or parameter called self-diffusion coefficient. So when we have the formation of absorbed film on the surface, this film should prevent and mitigate the passage and diffusion of corrosive species into the surface. So to estimate if an inhibitor can prevent the passage of corrosive species as compared to other inhibitors, we have to calculate the self-diffusion coefficient. And this can be conducted by atomic scale based method like molecular dynamic simulation. For example, here you have the main square displacement of corrosive species. Here is H3O in acidic solution. For example, here I can conclude that the inhibitor one can prevent the diffusion of this corrosive species. So inhibitor 1 can give better inhibition of metal, which is the reality. Return now to this. So here I would like discuss that, because I found this in many papers in the literature, that many authors use the radial distribution to conclude if they are chemical compounds. It's wrong. It's wrong. Why? As you tell you, the atomic scales based method did not consider the electron or the orbital. So how you can use the radial distribution function to conclude that they are here a formation of chemical bonds. It's wrong. Okay, because the method is based consider the electrostatic interaction and van der Waals interaction, and the electronic aspect is absent. They are not electronic aspects. So how you can conclude that they are the formation of chemical bonds? So this function or radial distribution function can just use it to calculate the interfacial distance and to tell if you have accurate absorption or not. But to use this function to conclude that they are the formation of chemical bonds is wrong. Let us now see. Okay. We move now to the quantitative structure property relationship. As you see in the beginning of this presentation, some indicator of reactivity like gap energy, delta N, can be correlated to the inhibition or to corrosion inhibition by a sample linear regression. But in some situation, you have to use more complex mathematical methods. For example, to use multilinear regression mathematical method. For example, here you have a mathematical model, which can use it to predict or to explain the obtained inhibition efficiency. For example, here you have the hardness of inhibitor molecules, total negative charge, and the energy of the formation of the inhibitor during the absorption process. So the use of QSPR approach in general is as follows. First, you should have a data set. This data set contains reactivity indicator, is the electronic properties of inhibitor and metal surface, plus the inhibition efficiency. In other words, you should have theoretical data and experimental data. And we will try to get the relationship here. What is the relationship to explain, to obtain this, for example, an equation which can help us to understand the inhibition presence. After that, we split the data into two different data sets. The first data set is the training data set, and the second one is the validation data set. This first data set is used for the training process. We choose, for example, here, I take here, for example, multilinear regression. We choose this data lead us to build a mathematical models which can relate the electronic properties of inhibitor and metal surface to the corrosion inhibition property. So here we obtain the QSAR model without validation. Here to confirm if they are not overfitting of model, we should perform a validation process. This is called external validation. This validation test is used to validate the obtained model. If we have good models, robust model, and credible models, we say that we have validated QSAR model. If you have not availed, you return the calculation from the first. But recently, there are a trend, which is an emergent field in this topic, in the use of artificial intelligence. There are many artificial intelligence like artificial neural network, support vector machine, genetic function approximation. These are the algorithm or the mathematical method which can be used to build a more complex model to predict or to understand the inhibition process. Because this classical mathematical model sometimes cannot give a better understanding of the collagen inhibition. For this, we move or we pass to use more complex model like artificial neural network. But the problem with this technique is the overfitting. You should avoid the overfitting, because if your model is overfitted, this means that you have a poor model. So, another thing, as you see here you have just what? You have intrinsic factors. The hardness here, the hardness, total negative charge, energy, all these factors relate to what? To the electronic property of inhibitor and metal surface. And what about the experimental condition? The concentration, because we know that the concentration of inhibitor can affect the inhibition. Also, the solution flow, the temperature. So, to get more performant model and representative model, we should also consider the intrinsic factor. So such approach called multi-physics model. Let's now give you example to how the use of this computational tools. For example, here this is a work which we conduct, which we have published recently in RTS Advances journal. So, in our study, we have tested the inhibition, the corrosion inhibition of an amino acid called, this amino acid, it is proline, which have carboxyl function and amine function. According to experience, we have found that the proline give better inhibition efficiency at neutral media, at neutral pH. But at acidic pH, we have get poor inhibition. So how we can, and what happened? How we can understand what happened here? So to understand that, we know that the proline is an amino acid. So you have his the protonation sit here and protonation sit here. So by changing the solution pH, surely the protonation state of the inhibitor will be changed. Another thing is the oxidation state of surface. By changing the solution pH, we affect the state of surface. For example, in acidic solution or acidic pH, the metal is consist of pure 10, but in neutral solution, the surface is covered by oxide thing. Also, the solution, we have to take in consideration also the solution composition, because the solution composition in acidic solution will be not the same in neutral. So, by considering these three factors, we have conducted a computational by using atomic scale techniques and electronic scale methods. So, what we found, for example, here, I will discuss, for example, here the gap energy. For example, here, at acidic solution, your inhibitor, his proline, is full protonated. Or sit here, you have a protonation of amine. What? This. You have a protonation of amine. And in near neutral solution, you have a deprotonation of carboxyl function. So by conducting the calculation, we have found that the gap energy of partial protonated proline is lower. This can lead us to understand why the proline give us a better cohesion inhibition in neutral solution. And we have a good correlation with these factors and the inhibition process. By using atomic scales, methods, we have conducted the calculation. What we have found? We have found that the full protonated proline did not absorb on the surface. As you see here, the interatomic distance between the inhibitors, this atom, and the surface is about 5.5 angstrom. So here, the inhibitor has at this state is more solvated on the solution and don't show a really affinity to absorb onto the surface. So, but at acidic pH, we have two forms, this and this. Here we have absorption, but according to the absorption energy, I don't list it here. The absorption is not favorable here. But when we move to near neutral solution, in which we have found the better corrosion inhibition, the absorption energy here is better than in acidic solution. Furthermore, as you can see here, the interatomic distance is very is lower than the first one here. So the interaction here is potent. So here you have you will form the inhibitor will form an adherent adsorbent film. So for this we have found better corrosion inhibition in near neutral solution as compared to in acidic solution. I forget to talk about the delta G of solvation. For example, here, see, for example, the full protonated form, according to this energy, is more solvated on the solution, which has been confirmed by this by the atomic scale method. So to conclude, the computational chemistry can be used by different approach or by different manner. So you can use the computational theory or the computational chemistry to understand or to explain the output of your systems. In other words, we can understand why an inhibitor gives an better inhibition as compared to another one. Also, the computational chemistry can be used before we do the experience. So, for example, here I return here. For example, here, after we obtain a validated QSAR model, we can design a novel amino or novel compounds. We design. We don't have to do the experience. We design novel derivative, and using this validated QSAR model, we can predict the inhibition efficiency of your newly designed derivative. And I think it's the end of my presentation. Thank you very much. And if you have any question, you can ask your question, or you can contact me directly by my email if you have any question about these topics. Thank you very much, dear sir.
Thank you so much, sir, for sharing your deep knowledge with us. I would now like to invite Dr. Ilyor Berdimurodov from Uzbekistan for his talk on the topic Green Corrosion Inhibitors, Types, Inhibition Properties, and Research Methodology. Before beginning of the talk, I would like to invite Mr. Amit Devangan sir to give brief introduction of our respected speaker. Sir.
Thank you, Sonali Loya ma'am. It is my great honor and pleasure to introduce Dr. Ilyor Badimu sir is an associate professor of chemistry at of Faculty of Natural Science, Kursi State University, Kursi, Uzbekistan. His research is mainly focused on the physical chemistry, corrosion science, material science, inorganic chemistry, organic synthesis, quantum chemical calculation, amdo simulation, and electrochemistry. He received Best Foreign Researcher Award, Taijin University, China in 2016. He is the author of several research papers, review articles, and book chapters in peer-reviewed international journals of RSC, Wiley, Elsevier, Spencer, and Taylor and Francis, etc. He has very good citation with an impressive H index and I-10 index. He is involved in many national and international projects. Thank you. Thank you.
Thank you so much, sir. Now I would request sir to begin his talk.
Okay, thank you. It's okay? Okay, wait. It's okay? Okay, thank you. I am Dr. Berdimurodov Ilyor from Karshi State University. I work at Department of Chemistry, Faculty of Natural Science in Karshi State University. It is my great pleasure to join your international conference named Emerging Fields in Chemistry Advancing Application. Thank you for all. Today I want to talk about my presentation named Green Corrosion Inhibitors and their types, their inhibition properties, and research methodology. Because why I select this name? Because nowadays corrosion is mainly an ongoing problems around the world. It is also dangerous ecological, economical problems in gas, in oil industry, electronic industry, in other automobile industry, in many. The corrosion problems is ongoing. Now is many research chemists try to create green corrosion inhibitors. Let me introduce our university. Our university is located in Kashkadir region in the south part of Uzbekistan. Our university has 8 faculties: social science, biology, foreign language, pedagogy, preschool and primary school education, physics and mathematics, in natural science and physical culture. There are around 600 professors and teachers have been working in 34 departments. In the current academic year, our 10,000 people enrolled, included 31 direction bachelors, around 10,000, and our 100 master's degree and undergrad and independent researchers. Here's our department, our department of chemistry. Our department of chemistry has a key faculty, key department in the Kashi State University. They have investigated especially nanomaterials, corrosion science, supramolecular chemistry, organic synthesis, physical and organic chemistry, polymer science, material science. Let me introduce about what is corrosion. First, corrosion of metals. You know, corrosion of metals is a large problem around the world because natural properties of metals, reduce it from corrosion. And for example, this picture, this metal pipes is corroded, and as a result, the natural properties of this metals lost. It is a very problem, especially economic and ecological problems. The second is the cost of corrosion. You know, the corrosion is a mainly problem in economical because, for example, in USA, every year USA lost $2.7 billion of their GDP. In India, 452 Arabic wallet many. Over 5% because Arabic wallets mainly their economy mainly based on gas and oil industry. The gas and oil industry has a huge problem with related to corrosion of metals. The China is also corrosion problems very large. In our country, corrosion problems also very high, around $1 million our economy loss, because our economy also based on gas and oil industries. Then corrosion inside of pipes and metallic constructions in buildings, it is very problem. You know, the corrosion problem is also affected the biodiversity, ecology, in other, for example, human lives. So corrosion inhibitors, it is a key achievement to protect metal materials from corrosion. Nowadays, there are many types of corrosion inhibitors, but nowadays there is many ecological and environmental researches on green corrosion inhibitors. What's the green corrosion inhibitors? For example, you know, flowers, for example, flowers. These flowers is natural plants in environment. Natural flowers has many chemical compounds. For example, oils, carbohydrates, some tetracyclic compounds in other organic compounds. So these flowers is not poison, not poison, and not disasters for ecology. First, you will select some flowers, plants, then you will extract from some chemicals from the plants, like this chemical. Then you can solute in solution, for example, water, because the solution is very important. For example, nowadays many corrosion inhibitors, solution is dangerous, like ethanol and acetone and other organic poison solutions. It's a very problem. Green corrosion inhibitors uses environmental friendly solvents like water and or ionic liquids. Then you will prepare the corrosion inhibitors, then you will enter in a corrosion solution, then corrosion inhibitors form resistant and or protective film or layer on the surface of steel materials. Then green corrosion inhibitors can protect steels or other metallic materials like copper, magnesium, aluminum, or others. They can effectively protect metal materials from corrosion. Then the corrosion inhibitors is green and cannot affect the environment. It is this green corrosion inhibitors. I select nowadays. I have find and I have read many articles nowadays because I am an expert in corrosion inhibitor science. Nowadays, there are 14 types of green corrosion inhibitors. These types of corrosion inhibitors nowadays are very famous, and many researchers attempt to research these green corrosion inhibitors. The first one, ionic liquids. Nowadays, many researchers interested to using ionic liquids, and in many research companies and factories will want to use ionic liquids. Why? Ionic liquids is a green corrosion inhibitors because it is biodegradable. It's not a poison. It's not poison, and it is not flammable. It is not. It is not volatile. It is very useful. It can protect many types of metal, like steel is iron-based, copper, aluminum, magnesium, and zinc, and other types of metals can protect it with the presence of ionic liquids. Ionic liquids has two parts. The first part, anodic parts, and the second part is cathodic parts. The first anodic parts can protect the anodic reaction of on the metal surface. The second part, cathodic part, can protect cathodic electrochemical corrosion reactions on the metal surface. The second one, carbon dots. Carbon dots also green corrosion inhibitors because it can many good properties related to green corrosion inhibitors. For example, it is biodegradable, it's not poison, it is good corrosion inhibitors. These carbon dots nowadays very new area in corrosion inhibition. There is maybe about lower 30 articles you will find in the Scopus of Webs and other research databases. This short carbohydrates. Carbohydrates also green corrosion inhibitors because it's sustainable and very green and biodegradable and very effective. Carbohydrates, but it is older green corrosion inhibitors. Nowadays, there is some modifications will occur. Hi, bro.
Sir, please share your comments like only first slide is visible, please.
Just visible, not so.
Yes, sir. Yes, sir.
Okay. Bro, I will join by my phone. By my phone. Please wait.
Okay, sir. Is there any problem?
I am joining by phone. Okay.
Okay, sir.
It's okay.
Mute your laptop. Mute your laptop.
Okay, it's okay.
Okay, it's okay.
Sorry, some problem with the sound system. It's okay. Okay, okay. Okay. Today I am talk about the main topic about green corrosion inhibitors and their types, inhibition properties, and research methodology. Let me introduce about our university. Our university, there is 8 faculties: social science, philology, foreign language, pedagogy, and preschool and primary school education, physics and mathematics, natural science, physical culture, and physical culture. There are around 600 professors and teachers have been working in 34 departments. In our academic year, there are over 10,000 people are enrolled, included 10,000 bachelors in the 31 direction, and our 100 master's degree and underground and other independent researchers. It's our department Department of Chemistry. This department is a key department in the Karshi State University. There mainly researches around green corrosion inhibitors, computational methods, physical and organic chemistry, polymer chemistry, supramolecular, and nanomaterial chemistry. First, I want to talk about what's corrosion and what's green corrosion inhibitors. Nowadays, you know, there is many types of corrosion inhibitors are using to protect metals from corrosion disasters and corrosion solutions, corrosion problems. First, you know, corrosion of metals is a very dangerous problem for manufacturers. This picture shows the corrosion disasters, corrosion destruction of metal pipes. You know, when the metals was distracted with corrosion problems, then this metals lose its natural properties. Then this metal pipes cannot usable. It's distracted. Then it is very large problems for gas and oil industry. The second, I will talk about the cost of corrosion. Around the world, every year, over $300 billion was used for corrosion protectors. There are some countries is dominant. For example, United States of America, around 2.7% of GDP. India, our 4%, Arabic world is 5%, because Arabic world economy is based on gas and oil industry. Then the corrosion problems are very, very problem. The last one is China. China also our every year China spend our 4% of GDP for corrosion problems. You know, in our country also corrosion cost of corrosion is very large, around $700 billion. Our country every year lost 700 million USD dollar. It is a very large problem. The corrosion problem is also dangerous for natural, like sea, natural atmosphere, and others. What's the green corrosion inhibitors? Nowadays, many types of corrosion inhibitors will use it to protect metals from corrosion problems. For example, imidazole based in other tetracyclase-based corrosion inhibitors. There are so many, but they are not green corrosion inhibitors because they are a little poison, some a little expensive, not biodegradable, flammable, or little poison for human beings in our other organisms. Green corrosion inhibitors have a good corrosion inhibition performance, like they are very good effective. They can absorb it on the metal surface with very effective, around 99%. Then they are also biodegradable, sustainable, not poison, not flammable, and very good soluble in corrosion solution. They can protect steel material, metallic materials, copper, zinc, magnesium, and other metallic materials very effectively. For example, you know this flowers. Flowers is natural part, natural plant. It cannot expensive, not poison. But these flowers contain many chemicals. These chemicals will be good corrosion inhibitors. Then you will restrict some flowers. Then you can flowers or other part of plants. Then you can extract some chemicals, some chemicals. These chemicals may be flavonoid or some organic compounds. Maybe organic compounds contains more active functional groups like amino, hydroxyl, and others. Then you can dilute this. You can mix it with solvent. Solvent is very important. Solvent is very important because the solvent may be dangerous, maybe not dangerous, maybe useful. You know, because the corrosion solution is mainly corrosion processes were occurred in mainly water phase, aqueous phase. Then your selected corrosion inhibitors can good soluble in water phase. Then this solution will add in corrosion solution. Then this corrosion inhibitors, green corrosion inhibitors, can attack on the surface of metal surface. Then it can easily absorb it on the metal surface to form it protective layer, protective or films. These protective films can cover on the surface of metal. This protective layer can protect steels from corrosion problems. Next one. Nowadays, there are many researchers interested to create and investigated green corrosion inhibitors. There are many types. I have searched. There are many types of green corrosion inhibitors, and I have classified around 14 types of green corrosion inhibitors. It is not published works. Now I am my research team working to publish these materials in some high-quality journals. First, we classified first one as ionic liquids. Ionic liquids is a green corrosion inhibitors because they are not poison. It's good absorbent and good inhibitors for metal surface. There are many research, over 10,000 researchers relate to ionic liquids. Ionic liquids have compounds has two parts. The first part anodic part, second one cathodic parts. The anodic part can protect anodic electrochemical reactions on the metal surface. The next part can protect cathodic electrochemical corrosion reactions on the metal surface. The second one, carbon dots. Carbon dots is a new trend in corrosion inhibitors. Maybe there are not many papers around around 50 papers maybe carbon dots because this is new area. Carbon dots also green corrosion inhibitors. They can protect metal surface with effectively over 90%. The next one is carbohydrates. The carbohydrates is an old topic, but nowadays is ongoing topic. There are some research teams are working to carbohydrates, especially carbohydrates modification. They can modify natural carbohydrates like Chitosan. The chitosan is a very useful carbohydrates green corrosion inhibitors. Next, molecular organic frameworks. This molecular organic frameworks also new trend in green corrosion inhibitors because they can protect also many types of metals like copper from corrosion very effectively. Metal molecular organic from Marcus is a complex, metal complex, but very good adsorbents. The 5 is medicinal or pharmaceutical drugs. Nowadays also is nutrient. Many research also relate to medicinal drugs in corrosion inhibition. But it's interesting. Nowadays, after medicinal drugs usage, the disasters discarded because they not use it. Use it medicinal drugs nowadays in a corrosion protection and will use it because they can protect metal surface very effectively. They have many good corrosion inhibition properties. The next one, plant extracts. Plant extracts is a well-known area. There is many research papers related to plant extracts. Plant extracts, it's natural products. They are not poison, not disastrous for environment. After use it for corrosion inhibitors, you can again recycling. It's not poison. It's we'll use it corrosion inhibitors. The 7 nano compounds. These nano compounds also nowadays many researchers created nano compounds based on natural products. For example, nano container, nano rods also will using as a green corrosion inhibitors. Why? Their protective surface is very large. Their protective surface is very large and very good water soluble and good absorbent. They can absorb it on the metal surface to form protective film on the metal surface, which this protective film is not soluble in corrosion solution. It's very effective compounds. The next one, 8. Heterocyclic compounds. Heterocyclic compounds also very useful because these compounds are also green corrosion inhibitors and contain many heteroatoms like sulfur, nitrogen, and oxygen or phosphorus. These heteroatoms rich or contain more p electrons. P electrons can protect metal surfaces because corrosion inhibitors chemically linked with metal surface. In this chemical way, p electrons is mainly responsible to form chemical bonds between corrosion inhibitors and metal surfaces. The next one, 9, inorganic compounds. Inorganic compounds also not also old and also well known because some metals, especially lanthanoid groups metals, and their compounds with some organic compounds or inorganic compounds also will using as a green corrosion inhibitors. The next one, 8, next one, 10, natural polymers. Natural polymers also well known and very effective corrosion inhibitors for metal surfaces. Natural polymers were extracted from natural plants from many researchers. This is the next one, natural oils. Natural oils also well known and a new topic in green corrosion inhibitors. For example, soil oils and other plant oils, some flower oils and many oils, very, very useful for metal protection. The next one, amino acids. Amino acids also well-known area. Nowadays, the amino acids were modified with some organic compounds to create green and efficient corrosion inhibitors. The last one, phytochemicals. Phytochemicals also nutrients in the green corrosion inhibitors. Some researchers relate to phytochemicals, but not many chemicals. These are also new areas. There is also other green corrosion inhibitors, but not well known, not many articles. It's very difficult to describe other green corrosion inhibitors. I want to introduce the main inhibition properties of green corrosion inhibitors for selection. For example, if you want to create some green corrosion inhibitors, then you will notice some important green corrosion inhibition properties. First one, this greenness. This greenness is very important for green corrosion inhibition properties. When you select some green corrosion inhibitors, then you will need to know green corrosion inhibitors need to be biodegradable, non-toxic, renewable, non-inflammable, and low volatile. It's very important because nowadays many environmental ecological restrictions around the world. They require green corrosion inhibitors. The next one, they have been high thermal and chemical stable in corrosion solution. It's very also next important properties because when you add your researched green corrosion inhibitors to corrosion solution, it can absorb on the metal surface and form protective film on the metal surface. The formed protective film need to be good thermal and chemical stable. Because it's not chemical stable or thermal is stable, then the formed protective film is destroyed, is soluble in the corrosion solution. It's largely important inhibition properties. The next one, good absorbance. Green corrosion inhibitors need to be good absorbent on the metal surface. The absorption properties of green corrosion inhibitors depends on types of metal types like copper, like steel, zinc, magnesium, or other metals. Some inhibitors very good absorbent for copper surface or others metals, others steel surface. Maybe not zinc or magnesium. The next one, solubility. Solubility also very important fact. Next important fact, because the corrosion of metals merely occurred in water phase. Then you will selected corrosion inhibitors need to be soluble in the corrosion solution. If not, it is not good inhibitors. The next one, green corrosion inhibitors need to contain more p electron-rich functional groups like amino, carboxyl, or hydroxyl functional groups. Why? These functional groups, p electrons of these functional groups are mainly responsible for corrosion inhibition properties. They can promote it to form chemical bonds on the metal surface between corrosion inhibitors and metal surface. This next one, heteroatoms like nitrogen, oxygen, sulfur, and phosphorus. You will selected green corrosion inhibitors need to contain more heteroatoms like nitrogen, oxygen, sulfur, and phosphorus. Why? These atoms can protect metal surface. They can support the absorption properties of metals. Corrosion inhibitors can form a protective film by p electron or heteroatoms. It's heteroatoms because corrosion inhibitors electrochemically connect the metal surface by chemical interaction and electrostatic interaction. Electrochemical interaction is very important. It's very stronger than electrostatic interaction. Electrochemical interaction is occurred by p electron-rich functional groups in more heteroatoms. The next one, green corrosion inhibitors need to contain more p systems like aromatic rings. These aromatic rings support and promote the inhibition properties and absorption properties of corrosion inhibitors. This is general inhibition properties of green corrosion inhibitors are very important on selected green corrosion inhibitors. Next presentation, I will talk about research methodology. Research methodology is very important on research on green corrosion inhibitors because many science some problems. How can research methodology in green corrosion inhibitors? Then I will talk about the key aspects in research methodology on green corrosion inhibitors. First, the first analysis gravimetric or V gravimetric analysis. This is next name weight loss analysis. It's very important. This first analysis. This analysis during this analysis, the effect of temperature, effect of concentration, effect of pH medium of solution in immersion times was calculated and investigated. The next, thermodynamics of activation in corrosion inhibition was investigated by gravimetric analysis. Then the difference of activation energy, difference of enthalpy, difference entropy of activation corrosion inhibition processes was calculated. These factors are very important. For example, this activation energy, the amount of activation energy can show the activation barrier on the metal surface. Corrosion inhibitors can form an activation barrier on the metal surfaces. Next one, enthalpy. Enthalpy is also very important because the corrosion processes or inhibition processes may be endothermic or exothermic. It's very important. This amount of enthalpy entropy can show the types of endothermic or exothermic nature. The last one, in the gravimetric analysis, it was also investigated that the absorption isotherms. Then there is many absorption isotherms. This most popular is Langmuir absorption isotherms. Then in using Langmuir isotherms, you can calculate the amounts of absorption constant and gives free energy of absorption and enthalpy and entropy of absorptions. These parameters are also very important. For example, the values of K absorption can show the equilibrium constant of absorption and desorption processes. The next analysis, after you have done gravimetric analysis, then you can do electrochemical analysis. Electrochemical analysis also very next important part on the green corrosion inhibition investigation. There are many types of electrochemical analysis. The main electrochemical analysis follows. For example, potential dynamic polarization, electrochemical impedance spectroscopy, electrochemical noise, electrochemical frequency modulation, cyclic voltammeter, linear polarization resistance. Electrochemical noise is an electrofrequency modulation is new techniques in electrochemical analysis. The two analysis is not distracted. The electrodes in your electrochemical equipment is not distracted with for this analysis. Why do you need this analysis? When this analysis was done, then some important factors was calculated. For example, electrochemical kinetics of cathotic and anodic process in the corrosion and inhibition was investigated. For example, the rate of corrosion, TAFL parameters, cathodic and anodic TAFL properties, in other properties was calculated. The next one, surface analysis. Surface analysis nowadays is a very neat analysis on the research of green corrosion inhibitors. There is many types of surface analysis. The first one, scanning electron microscope, atom force microscope, EDX or EDS, X-phase, XRD, VTR, and or Raman spectroscopy analysis. This analysis, why do you need this analysis? Same analysis can show the surface morphology of metal surface. After inhibition processes, metal surface protected or distracted. Then you can use easily by using same. AFM also. AFM can show the degree of protective layer. EDX, XRD also show the elemental and composition analysis on the metal surface. For example, after inhibition, the inhibitor formed some metal complex on the metal surface. Then you can analyze which components on the metal surface after corrosion or inhibition. Then
Sir, please.
It's okay?
Yes, sir.
Okay. Okay. The last one is short hair analysis. Theoretical analysis, there is many types of theoretical analysis, for example, DFT and Are you listening? Okay. The last one is your theoretical analysis on the green corrosion inhibitor. Nowadays, there are many types of theoretical analysis. The first one and very important is DFT calculation and DFT-B calculation. DFT-B calculation is a new trend in green corrosion inhibitors. It was easily calculate some merely properties of green corrosion inhibitors. For example, there are some analysis. Frontiers molecular orbitals, Foucault indicated optimization in molecular electrostatic potentials, the energy of LUMA and HAMA and other chemical reactivities. This last one is a molecular dynamic simulation. Molecular dynamic simulation can show the absorption of a metal isosurface. This theoretical analysis will now describe it. Dr. Braham, then I will talk about next presentation. Now I will talk about this mechanism in corrosion. This corrosion mechanism is widely known. There is many types of corrosion mechanisms we invited by researchers. Someone I will show the first, for example, if the corrosion solutions was being aqueous corrosion, then metal surface there is oxygen inside atmosphere can impact the corrosion repeat of metal surface. As a result of corrosion, some compounds like ferrium oxygen 3 and its oxidase in hydroxide form. This corrosion products is formed on the metal surface. They formed as rust. This rust can distract the metal surface. Next, how can corrosion inhibitors protect metal surface? For example, some researchers suggest some inhibition mechanisms. For example, this green corrosion inhibitors has the two parts. The first part polar head group, the second part hydrocarbon chain. When corrosion inhibitors added corrosion solution, then the first part polar head group absorbed on the metal surface, like this. This next part, hydrocarbon chains, this hydrocarbon chains protects metals
from corrosion destruction. Then corrosion steel pipes will known protect with corrosion inhibitors from corrosion ions like oxygen, carbon, and hydrogen sulfate. I would like to introduce the pictorial representation in the inhibition and absorption mechanisms. These mechanisms can show how can connect the inhibition mechanism to the structure of molecular structure of corrosion inhibitors. The corrosion inhibitors is metal sulfase. How can protect? How can link it with his structure? First, this guitar atom is sulfur. Sulfur contains more p electrons. The more p electrons was transferred or shared to d electrons, free or vacant d electrons of iron. Then chemical bonds formed between these heteroatoms and iron. This process is called chemosorption. The next one, rechemosorption. Then some hydroxyl atoms, some hydroxyl atoms also p electrons also transferred to vacant d orbitals. The next one, rechemosorption. In the rechemosorption, you know, p electrons system is like aromatic rings contain more p electrons. The p electrons also can transfer it to vacant d orbitals of iron. Also, this rechemosorption can support the absorption inhibition properties of corrosion inhibitors. So lastly, retrodonation process. Retrodonation, full d electrons of irons also simultaneously can transfer it to p aromatic systems. So you can also support chemical absorption and chemical inhibition process of corrosion inhibitors. If you need more information, you can visit our published works. The next one, I will show some theoretical analysis results related to our research works. When do you DFT analyze metals? You can calculate this optimization strategy in molecular electrostatic potential, LUMA and HOMA orbitals. Why do you need? These methods can show how can electronic structure depends on inhibition properties. How can calculate inhibition properties by theoretical methods? How can corrosion inhibitors protect metal surface? So can you answer in the DFT analysis? Also, some chemical reactivity like the energy of HOMA, LUMA, and the difference the energy of HOMA, LUMA, and electrostatic potential, nuclear philicity, electrophilicity, general hardness and softness, and other parameters, and also dipole moments. You can easily calculate. These parameters also can show the inhibition properties of some selected inhibitors. The DFT analysis will now be described by Professor Dr. Ibrahim. The next one I will introduce in the simulation. In the simulation, also very important to describe absorption properties of metal surface in absorption configuration of corrosion inhibitors on metal surface. Like, for example, these inhibitors. These inhibitors have two parts. The first part is a parallel absorption. The second one is a perpendicular absorption. It's very important, this configuration, because some inhibitors absorb it on the metal surface by parallel position. This parallel position, which inhibitor adsorbed on the metal surface perpendicular is inhibitor more good and very efficient inhibitors. FC parallel, it's not a good inhibitors, but when you raise the concentration, it can change the absorption position of inhibitors. The next one, relative concentration and other parameters can show the distance and the bond energy, bond length of metal, bond energy of bonds between metal surface and corrosion inhibitors. It's very important. For example, if the bond length is very low, then corrosion inhibitors very strongly or rigid absorbed on the metal surface. It's very large distance. It's impossible for good inhibitor. Let me introduce nowadays my research team. Nowadays, I have international research team. We have write some original articles, review articles in book chapters, and organize some international conference on seminars, and we will take together some researches. I have a research team, many research team. There are some research partners, some research friends. I will show the first one, Tianjin University, Professor Ji Wang, in Qatar University in Doha, Professor Abu Bakr and Abdullah, Chinese Academy of Science, very stronger professor, Professor Guo Shu, King Fahd University of Petroleum Minerals, Professor Emil B. Obod, also our partner. The next one, Tongren University, Professor Liu Gu, and some Marrakesh, Muhammad Riba, also my research team work. The next one, my friend from India, your country, Dakshwar Kumar Verma. The next one, national local universities, National University of Uzbekistan, Professor Khalid, Professor Akbarov, and also Morocco City, Muhammad bin Abdullah University, Professor Omar Dagdag. And I have theoretical research teams from Turkey, Savaskaya Cumhuriyet University of Health Service Vocation School. The next one, Professor Konstantin Katin from Russian Federation National Research Nuclear University. I have they are my research team. My research direction nowadays, some disciplines, for example, my research area nowadays, corrosion science and protection. We have many researchers and research papers nowadays. Also, some research are doing related to corrosion science protection. The next one, electrochemistry, surface analysis, and thermodynamics. The next one, organic and green synthesis. It's a very interesting area nowadays. We have some good and very effective organic compounds related to green synthesis methodology. The next one, absorption science in nanoscience. Nowadays, nanorodus, nanocontainers, carbon dots. We have interested and we have done some researches. So last one, supramolecular chemistry, also is very important for in pharmacy. If you interest our research team, you can join my research team. There is contact address or WhatsApp address. You can easily join our research team. I will show there are some our key publication, some best reputable journals like Arabian Journal of Chemistry, Journal of Molecular Liquids, Journal of Molecular Structures, especially Journal of Molecular Liquids. There are key publications. Our publications, for example, the first one, we will create some new corrosion inhibitors based on imidazole. Next one, we will introduce first one, gossipol derivative as a efficient corrosion inhibitors. This gossipal derivative is also green. It can extract from cotton oils. It's green corrosion inhibitors, very effective. We have introduced phase 1. As a conclusion, I am thank you for great attention, and I am very happy to join your international conference, and very much, and thank you for all. Thank you very much.
Thank you so much, sir. It was a wonderful presentation. Now I would like to invite Dr. Kamlesh Kumar Srivas, sir, from Pandit Ravi Shankar Shukla University, Raipur, to deliver his talk on the topic Design and Development of Paper-Based Chemical Sensors. Before beginning his talk, I would request Kuleshwar Patel, sir, to give brief introduction of our respected speaker.
Thank you, Sonali ma'am. It is my great honor and pleasure to introduce Dr. Kamlesh Srivas. He is an associate professor in School of Studies in Chemistry, Pandit Ravi Shankar Shukla University, Raipur. He has total citation of 2,510, which includes H index 29 and I-10 index 52. He has around 90 research papers published in international journals with average impact factor 3.5. He has been awarded many fellowships like JSS Fellowship, ORISC Fellowship, National Council of Science Fellowship, Taiwan, and National Council of Science Fellowship, CSIR Delhi. He is listed in the world top 2% Indian scientists 2019 in analytical chemistry. Thank you.
Thank you, sir. Now I would request Dr. Kamlesh Kumar Srivas, sir, to begin his session.
Thank you, Kuleshwar, for a brief introduction of mine. Now I think you people have heard two speaker, a nice speaker. So they have told about corrosion, and as we know that corrosion is a very important, and I think that is very challenging topic in research. As we know, across the world, okay, across the world, that means there are millions or billions of loss of money, okay, from across the world. And if you will do research in the corrosion, so that is very nice topic, okay. So now we will switch, okay, from corrosion to some sensor, chemical sensor. So I am Dr. Kamlesh Srivas from School of Studies in Chemistry, Pandit Ravi Shankar Shukla University. Good afternoon, one and all. Respected Dr. Omkar Lal Srivastava, Chairman of International Web Conference on an Emerging Field in Chemistry and Advances and Application, which is being organized by Government Kamala Devi Rathi Girls PG College, Rajnandgaon. And also I thank Organizing Secretary Dr. Dakeshwar K. Verma to invite me to give a lecture on this development of paper-based chemical sensor using noble matter nanoparticles. Before I want to tell that 2 or 3 times I have been visited, okay, Kamala College for a practical examination, and you may know that I am graduated from a science college Rajnandgaon in the year 1998. And I belongs to that place. You may know that village name is Gatla, and that is a very famous for a poha. This, I think nearby people are going to get, okay. So now I am going to deliver lecture on this paper-based chemical sensor. So generally, that my research group, okay, developing some analytical method for analysis of analysis of chemical substances from different type of samples. Maybe that may be biological, environmental, or food sample. And today, in this talk, I want to tell about just short introduction for synthesis of nanoparticle, how we can characterize a nanoparticle very shortly. Okay, and we will know what do you mean by sensor and how this sensor different types of sensor we are using in a daily life. And generally, this corona pandemic, COVID-19, we are using pulse oximeter. So this is an example of very simple sensor and how that we are using. Okay. And next, that in my research group, one of some people are developing a colorimetric sensor. So we will see what do you mean by colorimetric sensor and how these noble metal nanoparticles. We see that what type of a noble metal nanoparticles can be useful for a colorimetric sensing. And then we will see finally paper-based sensor means how. So this is a different, we can say, chronological order for development of any devices. So we know. So everyone, okay. So everyone in this universe wants, okay, happy life. So for being a happy life means we need a healthy body and a healthy mind. Okay. So and we will be very happy when we will get a good food, water, or air. Okay. But these food materials is contaminated due to the heavy industrialization, okay, or urbanization. So the food material or water or air may be contaminated. Okay, then this food material, water or air may be contaminated with these toxic metals or a toxic pollutant in air or some pesticide in food materials. So there are different types of technique or methods are available for analysis of these toxic chemical substances. Okay, but the disadvantage of this sophisticated analytical instrument may be very expensive. Okay, very expensive, and also that may be need a long time for a sample preparation and for a small laboratory for generally for a colleges. Okay, so that in remote areas or in our country there are many places or big university or institute there are no there is a lack of research facilities. So in this that if you don't have means minimum research facility, so means how we can do this type of work means we will develop a paper-based chemical sensor. Okay, so we will see how this paper-based chemical sensor can be developed in a remote areas in the absence of a sophisticated instrument. So as we know, this is an example. Okay, so this COVID-19, as we know, I think this is a used for a rapid test for a COVID-19 virus. So and this is not paper based. This is a means some kit is there. So generally we will see how. So this is also example of a sensor. Okay, we can say this is sensor. We will see how this work. Okay. Another one is in that that across the world people are increasing of this glucose. Okay, so that maybe that many people having that high concentration of blood sugar. Then how we can determine that blood sugar? Okay, generally this blood sugar. Generally, we bring some amount of blood onto the strip, and then this strip showing some reading, and this reading is based on the we know that glucose, okay, glucose getting oxidized in the presence of some oxidase enzyme, and the concentration of there is also okay simultaneously there is a release of electron, and this release of electron is proportional to the amount of that glucose present in blood sample. So in this way, the amount of glucose in a using glucometer can be determined. So these are simple type of sensor that are being used in a daily life. Okay. So now we will introduce that nanotechnology. I think many people may be now. So now nanotechnology is not means I think now many people are using this nanotechnology for their research work. Okay, and this nanotechnology is first introduced by Richard Feynman. Okay. This nanotechnology is the creation and manipulation of materials into nanoscale. Okay, and for this first time development, he got the Nobel Prize. Okay, and generally, okay. So the smallest unit, okay, if we are talking about a material, so the smallest unit of a nanomaterial we will call as nanoparticle, and generally the size of nanoparticle is 1 to 100 nanometer in a size. Okay. And here we can also see in nature, okay, there are several nanomaterials are present, okay, in the nature. So we know that this lizard, okay, can stick on a wall, and this is due to the nanofiber, okay, nanofiber present over the surface of a palm of this lizard, okay. Then another good example is this we can see in the nature, okay, beautiful butterflies, and these beautiful butterflies are due to the nanocrystal, okay, the nanocrystal which present on the surface of a feather, okay, so they reflect the light, so then we can see the shining, okay. Then another one is that nanostructure, okay, that COVID-19 virus, okay. So this is a same image from some patient from USA, okay. And this is a 3D image taken by scanning electron microscope. So we can, so as we know that, so that size of a COVID-19 virus is a nanometer, and we cannot see that size of that COVID-19 virus using a microscope. Okay, with that microscope, scanning electron microscope, we can see the 3D image. And another one we can see, okay, the size of this virus by cryotem. I think 4 or 5 years before, this cryotem has been developed, and the pioneer of this instrument, okay, got the Nobel Prize. Then this is another example of nanotechnology, the synthesis of a protein, okay, inside the cell. So this is a best example of nanotechnology. And we in the ancient history, okay. So I think this curve you have also before you have seen. So this curve is I think 1600 year old. Utilized thing like Kyrgyz curve, okay. So we can see, okay, different colors. When the colors from the back side, okay, when the light coming from back side, we can see the green color, and the front side we can see the red color. And the reason is due to the presence of a silver and a gold nanoparticle, which causes the different reflection, okay, different reflection when the incident light is coming on the curve, okay. Then also we know that in our country, okay, from ancient time that many bhasmas are being used. Still many people are using this bhasma for getting a cure of many diseases. Okay. Sorry. Here, okay. So here we can see the difference nanotechnology. So that our country from India first time that introduced nano car. So we can see, okay, what is the difference between nano? Okay, so we can see this that the size of this car is very big, and this is a very small. So okay, so these are the advantage of using nano car or nanomaterial. The size is very small. Okay, so we need very small to keep this material. Okay, very low cost. Okay, easy to access, low amount of energy. You can know this one require high amount of gasoline, and okay, then but they will do the same work and they need less space. So there are so many we can determine so many advantages compared to the big one. Okay, similarly that the use of nanomaterials. Okay, we have several types of advantage. Okay, so we can here also we can see one example. If you will synthesize 7 gram of nanoparticles, okay, of 4 nanomaterials, we can keep this nanoparticle full football stadium. We can make the layer of this 7 gram nanomaterials. So this means that if you use synthesize nanomaterial, so that will give high surface area, okay, for a different chemical reactivity. And that approach to synthesize nanomaterials. Okay, so this is suppose if you are synthesizing any material from big to small one. Okay, so that is called top down. So suppose if you want to prepare some idol of some god like Ganesh or Shankar. Okay, so if you will fill out, okay, that rocks, so that is called top down. Okay, and bottom up, suppose if you are starting from solving the puzzle is example of, okay, so this is a bottom up approach. So we are starting from small one to big one. Okay, so that is called bottom up approach. Synthesis of nanomaterials. Similarly, okay, so we know that this is a gold. Okay, suppose we know that the bulk gold is a yellow color. Okay, if we want to synthesize gold nanoparticle, okay, so here that nanoparticle is nothing but the accumulation of atoms. Okay, suppose that 0.1 nanometer size of gold means that there should be 13 approx. Okay, 13 atoms should be there. If you want to synthesize to 10 nanometer gold nanoparticle, so it should have a 293 of atoms. Okay, so this is called top of approach. In bottom of approach, we will take the precursor. Okay, that is salt of gold, and we will reduce this salt with sodium chlorhydride. Then that we will synthesize the pink color nanoparticle. So this is called bottom up approach for synthesis of a nanoparticle. Then different technique. Okay, so if you are telling that you are working on some nanoparticles, then we have to tell, means that we have to characterize the nanoparticles, whether we have the synthesized correct size, and also it is means getting with what materials and how it works. Okay, so generally, as I told, scanning electron microscope, we can see, okay, morphology of nanomaterials, okay, or 3D structure of nanomaterials. Transmission electron microscope, we can see the object, okay, size of nanomaterials. And XRD, we can know the crystalline structure, okay, crystalline structure, how the atoms are arranged in any nanomaterials. Okay, UV visible spectrophotometer is generally used for a monitoring, okay, monitoring of synthesis of nanoparticles based on a localized surface plasmon resonance. And thermal gravimetric analysis. as we know, if you want to synthesize any nanomaterials, we have to sterilize the nanomaterial with some capping agent, okay, and then we can check the stability of the capping agent on the surface of nanomaterials, okay. Then Fourier transform infrared spectroscopy. If you want to see the interaction of nanomaterials which is coated with some modifier, then we will see that a nanomaterials is coated with a means what type of a functional group, okay. Then last, atomic absorption spectroscopy, okay. So this is used for a determination of chemical composition of a nanoparticles, okay. Then that is scanning electron microscope. This is based on a that radiation of that electron, okay, from electron gun on the sample surface, and then we can getting that backscattered electron, secondary electron, and X-ray, okay, and that X-ray will tells about the composition of sample, backscattered will tells about the contrast in the composition of sample. So this is a difference in the scanning electron microscope and transmission electron microscope. Generally, scanning electron microscope, we are getting the signal, okay, above the sample surface. But in a transmission electron microscope, we can see after the sample surface, okay. And here we are generally getting the size of inverted image of the object. Then here, okay. So how we can determine sensor? What are sensor? So in sensor, generally we have a input signal, okay. Then the device senses. Then we are getting a output signal. So how we can understand? Suppose, okay, if you are touching any hot object by your finger. So finger we know that finger is a example of sensor, skin, okay. So that is sensor. So and hot is a input signal, okay. Then we will take out our finger from the hot object. So that is a output signal, okay. Then how we can define this sensor? So by American National Standard Institute, a device which provides a usable output in the response to specific stimuli. Okay, so that is called sensor, okay. And sensor may be optical, electrical, and mechanical. And also we have several types of a sensor or transducer like microphone, that what I am talking, okay. So that is microphone is also example of sensor, loudspeaker, and we have several biological sensor like touch, sight, okay. Then what are the quantities that we can sense by motion and position, velocity, acceleration, force, strain, pressure. So these are the different physical parameters that we can measure, and we can prepare sensor for these physical quantities. Okay, need for sensor. So we know that we have a biological sensor, tongue. You know that purpose of tongue, nose, eyes, skin, and you know that in automobiles, in cars, we have hundreds of sensors in a car. So suppose if you are want to close the door, so we can maybe pressing the key so that the door can close. We can rear that like maybe mirror, or maybe when that giving accelerator, okay. Okay, accelerator is also, so there are many, I think most of that consists of sensor, okay. Another one is that cell phone. We have different types of sensor for Wi-Fi. If you click the Wi-Fi, then okay. So like barometer, light sensor, touch sensor. So I think in cell phone we have different type of sensor, okay. Then we are also that TV, AC remote. This is also example of a pressure-based sensor, and also the traffic police are also using this type of sensor for determining the person is a drunkard. Okay, so there are different types of sensor in our daily life, and we can prepare this type of sensor. Okay. Another good example is a pulse oximeter. Okay, so you may know that this pulse oximeter based on a that near infrared. Okay, near infrared light. So here generally when we are keeping our finger, okay, inside this oximeter, then what is happening that infrared light, okay, passes through this finger, and in this finger we have a oxyhemoglobin and deoxyhemoglobin. Then the amount of oxyhemoglobin and deoxyhemoglobin absorb the infrared radiation. So here we can see the oxyhemoglobin. Okay, oxyhemoglobin absorb the infrared. Okay, near infrared this region, and that hemoglobin absorbed near the 750 nanometer. Okay. Based on that one, that oximeter will tells the amount of saturation value. Okay, means that how much amount of oxygen in your body. So this is a simple principle for working of a pulse oximeter. Okay. Then now we will come to the topic. Okay, colorimetry. So you know that colorimetry. What do you mean by colorimetry? So colorimetry means any object or chemical substance that is a colored. Okay, so that and if you will measure the quantitative, okay, with some instrument, so that is called colorimetry. And the wavelength for colorimetry is from a 400 to 800 nanometer. Okay, so here we will see simple example. Okay, simple example for a colorimetric determination of chemical substances that you can. Okay, this type of experiment you can ask for some that UG student or PG students in your lab. Okay, so if you have the colorimetry, and also that the cost of colorimetry is not very high. Okay, so okay, so this you know that glucose is determined, presence of glucose in any sample can be determined by Benedict reaction. Okay. And Benedict is composed of a sodium carbonate and a copper sulfate. So generally, if okay, that glucose sugar is present in your blood, so generally this will get oxidized in the presence of this Benedict reaction, and it will form a cupric ion, and okay, and also that cupric hydroxide and that cupric oxide. Okay, so this is a chemical reaction, and if so this is a molecular Benedict reaction, and if you are that high amount of that glucose, okay, glucose sugar is in your blood, so you will see this red color. Okay, due to the formation of cupric oxide. And if the concentration of the blood glucose is small in your blood, then we will see the green color. And based on this determination, you can determine the amount of glucose in a blood sample. This is another simple determination of a colorimetric determination. Okay, so this colorimetric determination of iron in a food sample, water sample, soil sample. So this type of a simple experiment can be asked. Okay, to PG student or UG student in a okay, where that means there we don't have a the big laboratory facility. Okay, so here we can determine that concentration of iron. Okay, so this work has been done by one of my the PG student. Okay, MSc student. So he drawn a standard calibration curve for a different concentration of iron, and using this standard calibration curve, they have determined the concentration of iron in different samples. Okay, but there are some disadvantages of this colorimetry. What may be the disadvantage of colorimetry? As we see that there may be high concentration. Okay, high amount of chemical reagents are used. Okay, here also, and also there are for a colorimetric determination, we are generally use a chromophoric reagent or some dyes, and these chromophoric reagent and dyes are sometimes harmful, okay, harmful for health. So this type of colorimetric determination should be avoided, okay. And this is another simple this is a paper-based, okay, paper-based colorimetric sensor. So we can say this is a color change, okay, color change of pH paper. When you are putting in a acidic condition, so you can get red color. When you are putting that pH paper in a basic condition, so you can see a blue color. So this is a simple example of a paper-based colorimetric sensor. And again, I can say, but this paper uses dyes, okay, and these dyes are sometimes harmful for our health. So here we see that colorimetric sensor, okay, that rapid test. So here that how it works. Here that this rapid kit, okay, consists of antigen, okay, antigen of a COVID-19 virus, okay, and when that is staff, okay, clinical staff putting the sample, blood sample from some patient, okay. So when that is blood sample of patient having the antibody, okay, of a COVID-19, okay, only give the color change. So that way this presence or absence of a COVID-19 can be identified, okay. Then okay, then nanoparticles. So now that our topic is about the use of nanomaterials for a paper-based colorimetric sensor. So generally, as we know that the bulk gold is yellow in color, okay, and the bulk silver is a that silvery. And the reason for this, why this is a yellow color and why it is a silver color, and this is due to the, because you can see that that silver, okay, silver, the bulk silver having a high reflection, okay, means this one having a high reflection, okay, means that what the light, okay, means coming to the this bulk silver, so it will reflect. So that is why we can see this bulk silver as a white, and the gold nanoparticle, it absorbs the maximum wavelength of light, and we can see the yellow color, okay. Then here that if you synthesize gold nanoparticle and the color is the pink, but the bulk gold is yellow, and we know that when you synthesize silver nanoparticle, then the color is yellow, but that bulk silver is a white color. And what is the reason? The reason is a localized surface plasmon resonance. Okay. So what is here? Okay, this terminology is very important in nanoparticles. So here generally the nanomaterials. Okay, nanomaterials absorb the UV or visible light. Okay, and there is a free oscillation. Okay, free oscillation of a electron cloud. Okay, causes the different color. Okay, from the bulk phase. So if you synthesize the nanoparticle, we can monitor, okay, monitor the localized surface plasma band, okay, in a UV visible region. And based, suppose, so here we can see, so this is a yellow color, and when we coming to the right side, then the color is changing, and due to this color change, maybe due to the increase in size of nanoparticle, okay, and we will also change rate, we will get a rate shift, okay, in a localized surface plasma band of a different nanoparticle, and this shift in a LSPR band for a nanoparticle can be used for determination of a chemical sensor, as a chemical sensor, okay. Similarly, for a gold nanoparticle, if you will synthesize these different size nanoparticle, we can check the rate shift, okay, rate shift of these nanoparticles. And okay, when you take some analyze, background noise. Hello. Okay. Okay. Okay, so here that now okay, so that my as I told that we some of my group people are using this nanoparticle, okay, as a colorimetric sensor, paper based sensor. So here how we are using this as a colorimetric sensor. Suppose if we put some analyte chemical substances, okay, and a particular chemical substance will okay cause the color change, okay, of gold nanoparticle from pink to another color, or from yellow from silver nanoparticle to some another color, okay. So that is very selective. We will see the selectivity for detection of some chemical substance, okay. So this is a one of our research paper, okay, where we have used silver nanoparticle for detection of a triazofus pesticide. As we know, these pesticides are very harmful, okay, for our health. As we know that the farmers or the people want to increase the increase the increase the increase the crop, okay, the crop production. So they are blindly putting the pesticide, okay. So here we have determined pesticide in some food and vegetable samples. So here we can see. So this is a glass vial containing a silver nanoparticle, and all the glass vial, okay, containing silver nanoparticle with a different pesticide. Here we have silver nanoparticle, then we have described the different pesticide, okay, but only the pesticide which containing triazofus showing the pink color, okay, and other pesticide did not show okay any color change, and also that this means around 400 nanometer we can see the LSPR band, okay, localized surface plasmon band, okay, but only the triazofus pesticide showed the color change, okay, color change of a silver nanoparticle with this pesticide, okay. So then we can use this change in a localized surface plasmon band, and also as well as a color change for a colorimetric sensing of this pesticide, okay. Then we have drawn a that is standard calibration curve. So if you want to determine quantitative determination, you have to draw a standard calibration curve, okay, for different concentration of pesticide into the silver nanoparticle. So this is a mechanism for a color change of a nanoparticle with this triazofus pesticide. So generally this triazofus pesticide containing a nitrogen and a sulfur group, and these have a good affinity, okay, with silver nanoparticle, okay. So then this will means this will effectively bind, okay, to the surface of a nanoparticle to cause the color change, and this will cause the color change as well as the aggregation of nanoparticles. So here, okay, aggregation of nanoparticle. So okay, then another one we have used gold nanoparticle, okay, and this gold nanoparticle is a capped with the lauryl sulfate, one surfactant, anionic surfactant, okay. Then when we added a arsenic into this gold nanoparticle, okay, then there is a aggregation of nanoparticle, and this aggregation of nanoparticle causes the color change of pink color to blue color, okay. And we have used this technique for determination of a arsenic in environmental samples of a Chhattisgarh region, okay. And this is again we can see the means we have added different metal ions into gold nanoparticle. Only the gold nanoparticle with arsenic 3, okay, only showed the color change. Also here we can also see that UV visible spectra, okay. Then we have a spike different concentration of arsenic into gold nanoparticle. Here we can again see when the concentration of arsenic is increased, then we can see the increase in color change in a blue color, okay. Then we have drawn standard calibration curve. Then in another paper we have used gold nanoparticle for determination of a cationic surfactant, okay, and this paper has been published in Microchemica, okay. Then so previously we are doing this type of work. Now we have stopped, okay, this type of work. Now why because here still we need a 2 to 3 ml, okay. As we know, we need a 2 to 3 ml of nanoparticles, okay, for a U-visible measurement. And this much amount of a nanoparticle is economically, okay, not good, okay. So now we are developing a paper-based colorimetric sensor, paper-based colorimetric sensor. So here now we are fabricating this nanoparticle on papers, and as I told, in colorimetric sensor we need 2 to 5 ml of nanoparticle solution. Here we just need a 10 microliter, okay, 10 microliter of nanoparticles. So we can say we have increased 200 times, okay, 200 times less, means use of a nanoparticle solution. And we know the advantage of paper. So this paper is the first thing is biodegradable, okay, eco-friendly and low cost, okay, and easy accessible, and also it is a flexible, okay. So there are many advantages of using paper-based sensor, okay. Recently we have published paper on a web on chip, okay, that is from RSC Journal, and here we have synthesized a coarse nanoparticle of copper and silver for detection of another pesticide, okay. But here in paper-based sensor we have used a smartphone, okay. So smartphone, I think most of people are using this device for several applications, okay. So we have used this smartphone for detection of a phenthroid pesticide from water samples. So there we have tried, okay, we have checked these different pesticide, okay, for a colorimetric detection on a paper substrate, okay. So here we can see this is a we have a, so these are a Whatman filter paper. We have cut this Whatman filter paper into a circle of 1 centimeter, okay, and we have the first deposited silver nanoparticle, okay, followed by the deposition of a different pesticide. You can see different types of pesticide, and the pesticide deposited with a phenthroid, okay, is showing the color change, means light is green, okay. So this is showing the selectivity for detection of a phenthroid pesticide from any type of samples, okay. Then we have taken this image using our smartphone. Then we have processed the signal. We have determined process this data in image software, or there are different apps available for a calculation of signal intensity, okay. So this is a schematic diagram. We have first taken the image of a paper substrate, then we have put this image file into image software for a calculation of signal intensity. Then we have again optimized this method for a means we have checked with a different smartphone like Note Pro 7, Note Pro 6, and Redmi A1, okay, of same megapixel camera. And you can see that signal intensity with the same megapixel camera showing almost same signal intensity. So you can use any of the smartphone for determination of it. Okay. Then we have again checked with a different paper substrate. So this is a paper substrate with Whatman filter paper, and also we have checked with a 41, 42 normal printing paper, and the best result was obtained with this Whatman filter paper number 1. Okay. Then we have also checked the different reaction time, and 4 to 5 minutes. Okay. Reaction time is sufficient for a detection of this pesticide. Okay. Then we have again optimized the effect of pH, and the acidic pH is good for the detection of a phenthroid pesticide, okay, on a paper substrate. This is a mechanism, okay, a mechanism for detection of a pesticide. Why the color is a change from a yellow to pinkish. So here this is the coarse nanoparticle, okay, which is a yellowish in color, okay, on the paper substrate. When we are adding a phenthroid pesticide, it shows the color change, and again the reason is due to the interaction of this pesticide with the surface core cell of this nanoparticle, okay, or causing the aggregation of nanoparticles. So here we can see this is a core cell nanoparticle. When you add this nanoparticle, okay, okay, when you add the benzoate into this porcelain nanoparticle, so that there is aggregation, and this aggregation causes the color change from yellow to dark pinkish. Okay, so this is a DLS measurement, dynamic light spectrum measurement. Then we have the Lita potential measurement, and we have also doing one of our collaborator, Dr. Santosh Singh Thakur from Guru Bhasidas, is doing this DFT calculation to prove the theoretical. So I have told, okay, that experimental approach for detection of a benzoate pesticide. So we can also validate our data with these theoretical studies. Then this is a calibration curve for determination of this pesticide. Then we have used this paper-based sensor for determination of pesticide, but we did not determine the benzoate. So we have a spike different concentration of this pesticide in a different samples. Okay. Then we have compared our method with the different techniques. So this is one of the method we have developed for determination of benzoate. Another method we have one of my research scholar, okay, Monisha. So she has developed a detection of iron in a environmental and biological samples. Okay. So here she has used again a smartphone. Okay. Means here she has synthesized silver nanoparticle kept with the CTAB. Okay. Then he spiked different concentration of iron, and when the different concentration of iron is increased, there is a decolorized. Okay. Decolorized in the color of a silver nanoparticle. Then we have a drawn standard calibration curve for determination of a iron from a different samples. So here we can see selectivity of the method. We can see these are the different paper strip containing different metal ions. Okay, and the paper strip with silver nanoparticle and iron. Showing the decolorized. Okay, so this is a selectivity for the determination of metal ion. Then we have a optimized the capping agent, CPC, citrate, CTAB. Then we have a selectivity for a determination of a iron. Okay, again we have also taken the UV visible spectrophotometric measurement. Only the silver nanoparticle with the iron showing the color change. Here we can also see the decrease in the UV visible spectra. Okay, so this is the TEM image. FTI spectra. Okay, so here also we can see the interaction of iron with the CTAB cap nanoparticle. This is a standard calibration curve. So here we can see as we increase the concentration of iron, there is a rise in the color of nanoparticle. Okay. Then we have applied this technique for determination of different water samples from this region, and also we have also determined the iron in a blood plasma. Okay, and we have also compared our result with the ICP AES technique. This is another technique used for a colorimetry paper-based detection of lead. Okay, from a different water samples. So now this slide is the end of my talk. So as we seen, okay, this paper-based colorimetric sensor are very simple, rapid, low cost, user friendly, and we can apply this technique as at the sample source, easy accessible, no training, user friendly. So there are several several advantages of using this technique. So they are my research group students, and here I think Tushar Khan and Tikeswari, they have selected for a assistant professor. Okay, thank you very much. So if you have any questions, so please ask me. Any question, any doubt? Hello, sir, Dr. Brahim. So, no question? Okay, thank you very much once again. Thank you very much for inviting me here to deliver lecture. And I wish you
Sir?
wish you all the best for coming session. Thank you very much.
Hi, sir.
Thank you.
Thank you so much, sir, for sharing your knowledge with us. Now, the first technical session has been completed. We would now start with our paper presentations. Today, we will have approximately 12 paper presentations. However, due to paucity of time, we would request the speakers to please limit their respective presentations within 5 minutes. All participants are requested to kindly take note of it. I request Dr. Kamlesh Kumar Srivastava to chair the session. I would now hand over the session to sir. We'll start with the paper presentations. Our first paper presenter is Mr. Satyesh Raj Anand from Central University of Allahabad, India. The title of his paper is Carbon Nanomaterials and its Applications. Okay, Kamlesh Srivastava, sir.
So, I think the first presentation is Satyesh Raj Anand.
Yes.
So, on carbon nanomaterials and its application. And for this session, I think you have to take 5 minutes. Okay.
Okay, sir.
Satyesh Raj Anand. Hello.
Hello. I'm here, sir.
You have to finish your presentation within 5 minutes. Okay. So we are running a shortage of time. Okay. So 5 minutes.
Okay, sir. Thank you for the. Hello, everyone. Good evening, everyone. I am here, the Satyesh Raj Anand, and my topic is the carbon nanomaterial and its application. Here, the well-known allotrope of the carbon before 1985 discovered graphite and diamond. Then the fullerene multi-walled carbon nanotube, carbon nano-onion, single-walled carbon nanotube, carbon nanorod, graphene, and carbon dot, and many undiscovered allotrope of the carbon yet to be discovered. But my focus in the carbon nanorod. Here, the synthesis of the carbon.
Please put in the slide mode. Okay. Full slide mode. Full slide mode. Okay.
Hello. Slide is visible. Hello. The synthesis of the nanocarbon mainly two methodology. First one is the conventional methodology such as the pulse laser ablation, arc discharge, pyrolytic method, catalytic method, and chemical vapor deposition. And second one is the non-conventional methodology such as the pyrolytic method. There are the two different ways such as the indoor and outdoor. Here, the carbon nanorods, the novel carbon nanorod were observed as a byproduct during the purification of the carbon nanotubes produced by the arc discharge process by Lee et al. In purification of the TM analysis and observed rod-like structure and diameter of the carbon nanorod were 15 to 50 nanometer, and other form of the carbon nanorod has been synthesized by the Chang et al. By the reacting with the carbon hexafluoride with the lithium catalyzed at a 523 Kelvin. The material shows the rod-like morphology with the dimension is the 0.1 to 0.5 micrometer width and 3 to 15 micrometer in length. Here in this slide, these are the general technique for the characterization of the nanocarbon, such as the scanning electron microscopic, transmission electron microscopic, atomic force microscopic for the morphological characterization, and in this continuation, the powder X-ray diffraction, Raman spectroscopic, X-ray photoelectron spectroscopic for the atomic molecular structure analysis, and last one is the UV visual spectroscopy, Fourier transform infrared spectroscopy, and nuclear magnetic resonance spectroscopy for the chemical structure analysis. Here, the overall scheme, the synthesized functionalized carbon nanorod used as two different applications, such as the selective sensing of the iron 3 and chromium 6 metal ion, and second one is the non-toxic behavior against the E. coli cells. Here, the synthesis mechanism of the FCNR, XPS, comparative Raman spectroscopy, and FTIR analysis. The simpler methodology used for the functionalization of the carbon nanorod by the EDA molecules to achieve the soluble functionalized carbon nanorod via the different synthetic methodology. Here, figure B shows the full XPS survey scan spectrum of the functionalized carbon nanorod, and there are the different elements such as the carbon, nitrogen, oxygen, and figure C shows the Raman spectroscopic analysis and the control sample of the oxidized CNR and after functionalization of the FCNR. The degree of the carbonization is the oxidized CNR is the 0.609 to reduce the after functionalization is the 0.339. And further the support the FTIR spectroscopic analysis, the comparative oxidized CNR and after functionalization of the carbon nanorod, and a significant characteristic property of the functional group, such as the carbon single bond nitrogen, nitrogen single bond hydrogen, and C double bond C and C single bond O is the presence of the functionalized carbon nanorod. Here, the full XPS survey scan spectroscopic analysis here A shows the correspond to the carbon, nitrogen, oxygen, and different composition of the elements. And here B, C, D is the short scan spectrum and different binding energy correspond to the carbon, nitrogen, and oxygen. Here, the comparative NMR analysis figure A shows the monomeric amine is the EDA molecule, and figure B is the schematic representation of the functionalized carbon nanorod, and figure C, D, E is the NMR spectroscopy analysis. Figure C shows the proton NMR spectroscopic analysis and the three different type of the spectrum, and figure D shows the D shows the carbon 13 NMR spectroscopy, and red rectangle box in the zoomed image in the figure E is the carbon 13 NMR signal and the significant carbonyl peaks. Here, the microscopic analysis figure A shows the FEACM image of the FCNR. FCNR is the functionalized carbon nanorod, and clearly shows the rod-like morphology, and figure B shows the diameter distribution histogram of the correspond to the figure A, and figure C is the TM analysis and the defected and mark with the arrow is the defect of the after functionalization of the carbon nanorod, and figure D is the short scans HRTM image and the graphitic fringes is the 0.3 nanometer in the presence. Here, the UV visual and fluorescence analysis figure A shows the UV visual spectrum, and figure B shows the here is the different excitation wavelength spectrum of the fluorescence, and figure C is the back excitation spectrum and different electron volt energy, and figure D shows the good photostable material. Here the selective sensing of the metal ion. Figure A.
Hello, Satyesh.
Ji sir.
Now I think you have to conclude within 1 minute, okay?
Okay. The selective sensing of the selective two different metal ions such as the iron 3 and chromium 6 metal ion, and figure C and E shows the fluorescence quenching spectrum of the iron 3 and chromium 6 metal ion, and figure D and F is the standard Stern-Bolmer plot of the FCNR against the concentration of the iron 3 and chromium 6 metal ion. Here the fluorescence quenching of the possible mechanism of the FCNR, and figure A shows the schematic representation and showing the two different sensing of the iron 3 and chromium 6 metal ion, and available of the d vacant orbital and the LM ligand metal charge transfer interaction. Here the biocompatibility assay for the FCNR over the E. coli cells and up to 9 mg per ml is the non-toxic behavior. Here the conclusion, the FCNR shows the excitation dependent emission at a blue-green region at a maximum emission situated at the 460 nanometer, and FCNR exhibit the excitation dependent emissive profile mostly in the blue-green region, which the used for the selective sensing of the iron 3 and chromium 6 metal ion, and the significant result in the limit of detection is the 45 nanometer and 11 nanometer respectively, and FCNR the proven to the non-toxic.
Yes, you have to end, I think.
Thank you, sir.
Yeah, okay. So, any question? Any question from any audience? Okay, thank you, Satyesh.
Okay, sir.
So, thank you, Satyesh, for a nice talk on carbon nanomaterials. Now we have another talk.
Thank you, sir.
Okay, thank you. So now we have another talk from Morocco. Okay, Dag Hayes. Okay, the talk is about fabrication of polymer-based epoxy resin. So he is there. Hello. He or she is there. Morocco. Eh?
Yes, sir, he is there.
Okay, so that topic is a fabrication of polymer-based epoxy resin as effective and a corrosive coating for steel computational modeling and post experimental studies. Some problem is there. We can continue with some other speaker. Facing problem. So I think he is facing some problem. Are we?
Hello, guys. We will say no from the result and together.
Or we will continue with some other speaker. Hello. Hello, Kumar. Hello.
Hello. Yes.
Yeah. So you are facing some problem. Now you can continue. I think maybe I think he not, maybe did not know means I think he should click the presentation. I think. Or we can continue with some other speaker.
Yes.
Hello. So another speaker is a Benson K. Mani from Bangalore. So okay. So topic is lithium and conductivity studies in a lithium phosphate based nanocomposite system. And sir, you can continue and you have 5 minutes time. Okay, so we have to finish all the things.
Okay, sir. Okay, sir.
Yeah, so please start.
Am I audible?
Yeah.
Okay. Good afternoon, everyone. Good evening. Thank you. I thank for first of all the organizer committee for giving me the chance and opportunity to present my work over here, this international forum. So my talk is lithium ion conductivity studies in lithium metaphosphate based nanocomposite system. Okay, so before moving to the topic, I have to give you a small introduction. What do you mean by super ionic conductors? Okay, or fast ionic conductors. So they are those class of materials which exhibits high ionic conductivity at room temperature. So we are focusing more on ionic conductivity, not on electronic conductivity. So basically, those materials which exhibit high ionic conductivity at room temperature comes under super ionic conductors, and this branch of physics or material science is called solid state ionics. So what are the figure of merits of these fast ion conductors? Obviously, they should exhibit high ionic conductivity and should have minimal or negligible electronic conductivity. And usually these materials have monovalent ion species which does all the ion mobility job, like lithium, sodium. Okay, and anions also we have like fluorine, oxygen. So why do we need these solid electrolytes? Okay, basically if you see, if you dissolve copper sulfate in water, and you will have easy mobility of motion of migration of this copper ions and sulfate ions. But then, is it same amount or same type of mobility is possible in solid? Well, it is hard, but then there are solid electrolytes which exhibit high ionic mobility. And why do we need these solid electrolytes? One of the simple reasons is, when was the last time we saw battery leakage happening in our mobile or in your laptop? Okay, it's like 20 years ago this problem was common, but nowadays we don't come across this leakage problem because all our batteries are using solid polymer electrolytes. Again, they are solids. Okay, and then because they are solids, these electrolytes can be used in a very vast range of temperature and pressures also, because liquids they need to boil off at high temperature. Plus they have long storage lifespan, and few of the solid electrolytes do exhibit good high ionic conductivity. For example, rubidium Ag4I5. So based on these structures, microstructures, we can have a lot of different classes of solid electrolytes like polycrystalline, and then we can have composites. Okay, like polycrystalline added with some nanofillers and all. So those are called composite electrolytes. Then we can have glassy electrolytes. That means actually glasses which can conduct ionic conductivity exhibit. And then we have the common polymer electrolytes, which all of us are carrying in our mobiles and laptop. The batteries which we are using, they are polymer electrolyte based. Okay. So I'll skip over because of the shortage of time. So basically, my choice of material today I'm taking is a lithium metaphosphate, that is LiPo3, which is purely a ionic conductor, but not so good ionic conductor. The ionic conductivity is not what is a appreciable type. The aim is how to enhance that conductivity. Okay, so one of the way is by heterogeneous doping. That is, you take the material and dope with disperse these nanofillers, inert oxides, submicron or nanosize, SiO2 silicon or Al2O3, and like that you can actually enhance the ionic conductivity. Or another way of doing the same thing is by homogeneous doping. That is, you take a element impurity, okay, and in that case you generate either the interstitial ions or vacancies. So for the ease of ion migration. Yeah. So application, as I said, the solid electrolytes covers the batteries, solid oxide fuel cell, electrochromic display windows, supercapacitors nowadays. Okay. Yeah. So this is my material, lithium metaphosphate, not so good material, but as I said, the end of the day, the aim is how to enhance the conductivity. So one method is heterogeneous doping, that is using 60 nanometer size aluminum oxide with 10 mole percentage weight. And second method is you actually introduce barium, that's a divalent ion inside the material. So you can generate the vacancies. So the typical preparation method was using lithium carbonate and ammonium dihydrogen phosphate, and you have your LiPo3, pure LiPo3, and then by mechanical mixing you can add these nanofillers to it, to LiPo3, or in the stage of the preparation itself you can add barium nitrate to have a equivalently doped LiPo3. Okay, so these are static figures.
The slide is not moving, sir. Slide.
There.
Your slide
It's
is
not moving?
No, I think it is stable. I think stable.
But now is it moving now?
Yeah, now is okay. Now okay.
Okay, when I go to that full screen mode, then it is not moving actually. Now it is moving?
Yeah.
I think I will keep it like this itself. Okay. Yeah, so this is the XRD image of the lithium metaphosphate which we have prepared, and it confirms with the formation that yes, the material which is formed is pure LiPo3, and this is the XRD images of the eluvalent doped and homogeneously doped and heterogeneously doped LiPo3, and the XRD images shows that the doping has not changed the structure of LiPo3. That means the Al2O3 and barium nitrate has not change the structure of LiPo3 in any manner. So basically it's LiPo3 with inert fillers, LiPo3 with barium nitrate doping. And then Raman spectra also shows the typical POP chain stretching, POP strain shoulder, and PA double bond O stretching, and which is typical of LiPo3. Okay, so we don't have any anything extra or any other bond formation in our material sample. So it goes well with the literature survey also. And this is the main impedance spectroscopy by which we are actually calculating or finding out, determining the conductivity property, how good it has become. So for example, okay, so you can see the impedance plot or Nyquist plot. The larger the semicircle, the higher the resistance. Lesser the semicircle.
Time is over.
Okay, so basically end of the day, this is the doping sem which I wanted to show. This one is with a pure LiPo3. This one is a doping, and the doping actually enhanced the conductivity by 2 orders. That is the conclusion. Doping with nano doping, nano Al2O3, 60 nanometer size, actually enhanced the ionic conductivity by 2 orders. That is the main takeaway from this research work.
So thank you, Ben sir, for a nice presentation on lithium ion. Okay. So
yeah, thank you, sir.
Okay, so I think we have shortage of time. So I think anyone maybe want to discuss our question, maybe later on they can contact through email. So now we
Sure,
have,
sir. Sure, sir.
so we have shortage of time. So we have another speaker, Janita Saji from Bangalore. So she will talk about enhanced thermal properties of a polydimethyl silicone nanocomposite. Yes, sir.
Yes, sir.
Right. Okay.
Okay, sir. Yeah, yes. Yes, sir. Okay, sir. Okay. No issue.
I am present. I am present.
Yes, sir. Visible.
Okay, good. Okay, I will do. Hello everyone. Thank you, Mr. President, Honorable Assistants. I have the honor to present my presentation to you, which is entitled Fabrication of Polymer Based Epoxy Resin as Effective Anti-Corrosive Coating for Steel, Computational Modeling Reinforced Experimental Studies. Next, next slide. Next slide. Next slide. Yes. Yes. Okay. The presentation is divided in several sections such as objective introduction, material and method, result and description, and finally conclusion. Next, next slide. Okay. The objective in this study is to develop an anti-corrosive coating material for carbon steel corrosion in 3% in ACA medium. Next. Next slide, please. Let's begin with the introduction of the presentation. Next, please. The materials can be divided as thermoplastic polymers such as polyethylene, elastomer such as polyisoprene, and thermotank polymers such as polyepoxy. The term epoxy resin designed a wide variety of polymers containing one or more epoxy groups. The preparation of polyepoxy can be carried out according to the main route by epoxidation of polyunsaturated compounds in the presence of a oxidant or by the condition of epichlorohydrin with the compound coating at least two mobile hydrogen such as diol, diamine, and polyphenol. Next. Curing of epoxy resin is an exothermic reaction and in some cases products sufficient heat to cause thermal degradation. Curing can be achieved by reacting in epoxy with homopolymerization or by forming an copolymer with polyfunction creative agents or handles as amines and anhydrous. Next. So epoxy resin is widely used in several industrial fields such as tooling and additive, electrical, electronics, civil engineering, structural composites, and coating. Next slide. The coating eventuates according to their chemical structure by forming an impermeable polymer film which could adhere well to the metal surface and having good chemical stability. Next. We now continue in our presentation by morning methods. The second chapter concerns the materials, method, and characterization technique that we used further and achieve the result obtained in this work. Next slide. The formulation Jida MDA consists the curing of an epoxy resin Jida with methylene dianylate MDA. Next. Next slide. Yes. Consequence of performance of the coaching was analyzed using potential dynamic polarization and electrochemical impedance spectroscopy, competence energy station using molecular dynamic and density function theory. Next, next, the third chapter presents the results and discussion. The polarization pathway, anode and cathode curve for carbon steel for the epoxy coating applied on carbon steel in 3% in ACF solution without and with GEDA MDA are shown in figure and table. The GEDA MDA acted as effective anti-corrosive coating material with the highest protection efficiency of approximately 19%. The PDP results showed that GEDA MDA affects the rate of anodic as well as cathodic reaction with major influence on the cathodic region. Next slide. The Necus plots for the epoxy coating applied on carbon steel in 3% solution without and with GEDA MDA are shown in figure and table. Results and order of the protection effect of the GEDA MDA showed the maximum efficiency is 93%. This would be attributed to the high efficiency of the barrier coating and were from its unvariable nature. Next slide. Next slide. Yes. No. Before. No problem. No. In this simulation, demonstrated that GEDA MDA acted as effective adsorbate and occurs to flat or horizontal orientation over the metallic surface. Next slide. In present study, the epoxy coating on GEDA MDA was prepared and evaluated as effective anti-corrosion coating for carbon steel corrosion. Following conclusions were drawn from the study. The PDF shows that the protection efficiency for the GEDA MDA about of 93%. ES study showed an excellent performance of the GEDA MDA as effective anti-corrosive coating at metal electronic interface. In this simulation, that GEDA MDA strongly and freely gets adopted on surface aromatic and amine and hydroxide. Thank you very much for your attention. Thank you.
Thank you, Amar, for your presentation. Now we have another speaker, Janita Saji. So continue, madam.
Yes, sir. Thank you, sir.
My name Dr. Rajkumar Gupta. When it is, I think it's fourth number, no?
Sir,
Hello?
can you see PPT? Sir, can you?
Okay. After that, ma'am, na? Okay.
Sir, please exit from the PowerPoint presentation. Exit.
Sir, can you see PPT?
No, I think please first exit that Umar presentation. Okay. Now, now you can present, madam.
Okay, sir.
So you have 5 minutes. 5 minutes.
Can you see, sir?
Yes.
Yes, sir. Sir, can you see my PPT?
Yeah. So continue, madam.
Yeah.
So please summarize your work within 5 minutes.
Yes, sir.
Please summarize your work within 5 minutes. 5 minutes.
Okay, in PPT mode, right? Okay, sir. Thank you, sir. So, first of all, sir, I wanted to thank you all that you have accepted my paper. So, good evening, all. So my topic of presentation is enhanced thermal properties of polydimethyl siloxane nanocomposites. Is it visible, sir? PPT?
Yes, yes.
Yes, ma'am. Yes, ma'am.
So, introduction of the paper is nanocomposite. As we all know that nanocomposites are a class of material which contains at least one filler dimension in a nanometer range. So based on the filler geometries, so nanocomposites can be classified into the three categories. Number one is called three dimensions. The example is fumed silicon dioxide and nanometallic powder. And number two types is carbon nanotubes and whisker possesses two dimension in the nanometer range. And the third one is a 1 nanometer range. For example is clay, mica, expanded graphite, etc. So in my research topic, I have chosen the nanographite as a filler. As we all know that nanographite is one of the allotropes of carbon. So it is made up of different types of layer of single carbon atom, which is actually thick, which is thick and which is known as graphene. So graphites are characterized into the three types. The first one is the crystalline graphite, second one is the lump graphite, and the third one is a amorphous graphite. So this nanographite shows a similar layer structure and it has a very high aspect ratio. Its ratio about 1000 to 1500. So my present work is actually based on the nanocomposite. So I have chosen the silicon material or PDMS, polydimethyl siloxane, and I added the filler. So present investigation is focused on the analysis of the rubber compounds on the thermal studies. And the composition analysis I have taken and different studies is done. And under that studies, I have done the TGA, thermogravimetric analysis. I have done the DTG also and also done the DSC studies. So I have taken this materials, polydimethyl siloxane, PDMS, which is also known as a silicon rubber. And filler, as I told you, I have taken the nanographite and dicumul peroxide. It's a curing agent, and the other ingredient is zinc oxide and the steric oxide. So compounding and sample preparation, all the compounds mixed with the other ingredient in a Brabender plastic order, which is a laboratory size is 225 into 100 nanometer, and it is mixed in the 2-roll mixing mill. And the temperature range I have kept around, it's a 65 to 70 degree and by carefully circulating water. After the mixing, the elastomer composition were molded at around a 160 degree temperature, and we used electrical heated hydraulic press, and we get a sample it's a prepared sample is a molded form. So this I have taken the composition, as you see here, the formulation of unfilled and nanographite filled nanocomposite. So nanographite, I have taken the variation proportion. It is 0 to 468 ratios I have taken. So the coming to the characterization portion, the cell studies you can see in the PPT. It's excellent distribution of nanographite in the PDMS matrix. You can see here all the four images. It shows that excellent distribution. The nanographite is randomly oriented throughout the PDMS matrix, and we can see that very small agglomerates appear due to the increase of the weight percentage, which is obvious because once we increase the weight percentage, the agglomeration will be there. So in 8 PHR loading, we can see that the few agglomerations are there. Same with the TEM analysis also. The very good exploration of the nanographite within the PDMS matrix, we can see that a very some region we can see that the small agglomerates are there, which is to be expected because when we increase the nanographite loading, so obviously it will be there. So in case of 6 PHR and 8 PHR loadings, more and more the larger amount of agglomerates were observed. And This indicates that the decreasing dispersion of PDMS matrix with an increase in the nanographite loading. And the average diameter of nanographite, which through the HRTM analysis we got, that is approximately 25 nanometer size. Differential scano.
You have 1 minute. 1 minute.
Okay, sir. Okay, sir. So differential calorimeter, scanning calorimeter, we can see that we have noted the transition temperature. It is approximately minus 70 degree centigrade. And we can see in the diagram also, in the graph also, that the glass transition temperature, that is a minus 70 degree. And it is also seen that the temperature of crystallization as well as the degree of crystallization, which is actually the area measured under the peak, it decreases when we increase the nanographite loading. And this is only because of the cross-linking density due to the polymer filler interaction. So next slide is all about the thermogravity analysis. So initial weight loss, we can see around the 300 to 400 degrees centigrade. And next weight loss is 450 to 550 degrees centigrade range, due to which the very first is the 300 to 400 degrees centigrade. It means that this is because of due to loss of the volatile matter present in the composition, or whereas in the 450 to 550 degree, that is because of the medium volatile elastomeric component present in the composition. So next slide is all about the differential thermogravity analysis. So here we can see that in each graph there is a 2 peak, and that is the temperature is written here, that once the 2 PHR we got that 407 and 528, and 4 PHR 432 and 544, and so on. And it is significantly increased. So the result indicates that the addition of the nanographite significantly increase the thermal stability of the silicon or PDMS in the nitrogen atmosphere. So next slide is all about the conclusion, which I don't want to repeat it again. Thank you, sir. Thank you.
Thank you, madam, for your presentation.
Yeah, thank you, sir.
Yeah. Now we have another speaker, Rajkumar Gupta.
Yes, sir.
So the topic is a power factor of a thermoelectric SiO2 nanoparticles of a thermoelectric behavior of a CH3, CO4, so on. Okay, so please, sir, proceed, sir. So you have to finish within 5 minutes.
Yes, sir. Sir, I have sent my that poster. If you just please put this poster on the screen.
So, hello, Dageshwar. Dageshwar Verma. Hello.
Yes, sir.
Yes, so please, sir. So who is a...
Please put my poster, Rajkumar Gupta poster.
Acha.
On the screen, sir. Thank you.
You have that poster in your place, in your laptop. Hello.
Yes, sir. I have a laptop.
No, you have that poster. You can directly so.
I'm trying.
If you have in your laptop, you can directly show. Sergeant, you have to.
Just a second, sir.
Please show from your laptop, sir. Here it is not visible.
Okay, sir. I'm trying. Just give me a minute.
So you have to click present now button. Present now.
Yes, sir. Just a second. I think this PPT is shared. Hello.
Okay.
Thank you. Good evening to all. My name is Rajkumar Gupta. I am assistant professor in Sardar Vallabhbhai Patel College. Today my topic on power factor of thermoelectric silicon dioxide nanoparticles adopt thermoelectric behavior of their influence in calcium cobalt oxide. Basically, this layers cobalt oxide is a thermoelectric material which is used for energy harvesting and heat conversion applications because of its good thermoelectric properties and the fact that the raw material calcium and cobalt are non-toxic, abundantly available, and expensive. Calcium cobalt oxide powders are prepared from solid state methods. The effect of this processing on microstructure and thermoelectric properties of these ceramics shows that it is highly give thermoelectric properties by giving uniaxial pressure of 70 megapascal and then heated for performance of 880 degrees Celsius for 24 hours. The structural characterizations of pellets were carried out by X-ray diffractions XRD, which matches with JPTS data 0002301110, and EDX confirmed the stoichiometric ratio of calcium cobalt oxide and the presence of silicon oxide in the sample. Microstructures imaging reveals compactness of connectivity among grains with the estimated density using Archimedes principles suggests that the formation is nearly 92% of with this relative density for the new pellets ceramics. After the making pallet, we measure the thermoelectric measurement. The electrical resistivity shows that the compost have 218 microvolt per Kelvin, and the Seebeck coefficient shows that high value at 700 Kelvin, which is accomplished by the silicon dioxide present in calcium cobalt oxide sample. A maximum composition sample containing 0.2 weight% shows that power factor of about 32% by this measurement. I can't show my PPT because I can't handle with this, but I show with this structure. Have you seen my PPTs here?
No, only I think Word file. I think
This Word file, no? Sorry, I can't adjust myself with this PPT.
You have finished. You have finished, I think.
Basically, I just showed that the thermoelectric materials is very easy to prepare. Oxide thermoelectric material, that is calcium cobalt oxide, and it shows high power factor and shows high jetty factor, which is very useful in the recent day, as we see that so many vehicles and automobiles are electric uses, and these all electric cars, their thermoelectric materials are used. Thank you. If there is any question there.
Hello. Thank you very much to all presenters and our chairperson of this session. Because of the lack of time today, I request all the other remaining participants from serial number 6 to 12 that they will present at 1 p.m. tomorrow and present their paper in serial wise. Okay, very much thank you, sir.
Thank you, sir.
I invite Kuleshwar Patel for thanks.
Hello, Awadan. Thank you, Sachin. I would like to thank Professor Rahim Al Ibrahimi sir, Dr. Eliur Badimudu sir, and chairperson of this session, Dr. Kamlesh Kumar Srivastava sir, and all the presenter and participant who participated and attended this conference. So with this, I announce the end of today's program. All the participants are requested to join the session again tomorrow at 12:45 p.m. Thank you, all of you. Thanks.